So, let's get this started. Thank you everyone for coming. It's nice to see a lot of people here. We're going to have 3 days of presentations by most of the people in this room. I just want to give you bits and pieces of information before Samuel comes and presents the death of the PNCG. No? So first of all, for Wi-Fi, I guess almost every one of you has Azure Roam, but if for some reason you cannot use Azure Roam, you can have a temporary Wi-Fi account, and to get that you should talk to Nicolas, who is there in the blue shirt with his headphones on. He will get you a Wi-Fi account, but if you can use Azure Roam, just use that. For the talks, we are using Zoom just to project onto the screen behind me, where you can see multiple instances of me. And we are live streaming the talks online. So people are able to watch your talks on YouTube with about 20-second delay, but they are not able to interact. They are not able to ask questions online. The questions are only from inside the room. For the talks, I think I explained everything to the speakers. You just connect to the Zoom session that we have running for the 3 days, and you share a screen, and then you're good to give the talk. Alternatively, you can give me a PDF or a keynote or a PowerPoint, and we'll use this backup to show the talk. For lunch, we had enough money left over to give you a coupon for lunch in the canteen, which is like right next door here in the park, for 1 day. So the coupon you can find in the back of your badge. You just present that in the canteen and you get your lunch. And you can choose whether you use it tomorrow or on Wednesday. For the other lunch, we've made some recommendations for restaurants that are nearby for having lunch. So you can go on the webpage, on the conference webpage, and look for suggestions there. Most of them are within 10 minutes walk. Generally, if you walk a bit to the south, you go to the end of the street, you'll find a kind of a cluster of restaurants that are frequented by people at ENS. So for the important thing, for the wine and cheese, which is tomorrow, we will do that at the Observatoire. So CRAL, Centre de Recherche Astrophysique de Lyon, I think is one of the smallest institutes in France, yet we managed to be split in 2 locations. So one is here at ENS, where we have about 1/3 of the staff, and 2/3 are at the Observatoire, which is 7-8 kilometers outside of Lyon, on a nice hill, a beautiful old site where people used to do observations. So the plan is, tomorrow, after we finish here around 5:30, we all go, everyone that wants to join the wine and cheese, we go to the metro station, which is right next door to us. We take the metro to the end station, 3 stations from here, and then there is a bus picking us up to go to the Observatoire, which is about a 10-minute drive. The forecast is absolutely horrible tomorrow. It's supposed to clear up around 6. So if the weather forecast is perfectly accurate, then we'll go to the Observatoire, and as we arrive there, the sun breaks out and it will be perfect. Chances are that won't happen at all. We have to see. Anyway, I mean, it's very nice to be outside at the Observatoire, but we will have the wine and cheese inside in the local social, where we can be dry. For the badges, when you leave the conference, it would be nice if you leave them behind, so that we can recycle them for whatever next conference we have here in Lyon. So just put them on the table in front. Okay. I think one more thing for the posters. There are 4 or 5 posters that people have. bring them to Jeremy Fench with a raised hand over here, and he will help you put them up on the grills standing right there. I think there are 4. There are 4 grills, so there should be 4 posters. That's about it for instructions. Maybe if someone has questions, I can try to answer them. Otherwise, you can always come to me or one of the LUC. We have special badges in the LUC. We have like these blue ellipses to mark us out. So if you look for these blue ellipses, you find the LUC. And you can ask them if you have any questions. Okay, so then we start with Samuel. Okay. If you need a laser, there's one here.
Oh, okay. Yeah, I guess that should work, right. Okay, so thank you for the introduction, and thank you for everyone for being here. It's nice to see a full room, so kind of welcome you to the last PNCG days ever. But of course I will come back to that later. Initially I was asked to give a review a bit of what we do and what are the current evolutions, and the evolution got very quick, so indeed we are not PNCG anymore already, but anyway. Before forgetting, I wanted to give thanks to a few people, so the organizer in Lyon, especially Joachim and Nicolas, who have been organizing everything. So I guess everything is going to go very well, except the weather, but thank you. And since it's a historical event, I thank everyone that I forgot to thank in the previous times. So all the CS, the current bureau, which is the PNCG, we have a bureau, so I'm director, but Mathieu Tristram and Benjamin Magnelli are together with me in this story, and we do everything together. So Benjamin is here somewhere at the back, and Mathieu is not here because he is at the CNES perspective representing us. And of course, I put also the past directors because I inherited PNCG from Vanessa, who got it from Stéphane Charlot before, and thank you for being there and for being a nice community. Since it's a historical event, I went a bit back in history. So 100 years ago, actually, here you can see Hubble showing off with the Andromeda galaxy that he discovered was a galaxy. So basically, our field started at that time, 100 years ago. So it's nice to finish PNCG 100 years ago, 100 years after this historical discovery. Since then, there has been a lot of evolution in the community to organize ourselves. So there was some GDR, maybe the oldest person in the audience can remember them, but not many people, obviously. There was one on Cosmologie, then it became a programme national, then there was one in Galaxies that became a programme national, then the two were merged at some point in 2008. And recently, there was a new GDR that started, that is a GDR of Cosmologie, at the initiative more of the EN2P3 people, but we are part of the story, so we try to work in good harmony with them. And then this year we learned that it's the end of the PNCG. But of course, next year it's the start of the PNAA. So before you are totally lost in these acronyms and everything, I'll try to warn you a bit about this change. So PNEEAA means Programme National Astronomy and Astrophysics. So it's everything basically, except planets, which are separate. And within the PNAA, there will be Action Thematics, 80. And there should be a NATI-CG. That sounds like DNA, but it's not related. Okay, so I have a slide on our past missions, but in fact it will be, of course, probably the new PNAA is going to embrace those missions too in a slightly different form. So I will try to explain you a bit how it's going to change, but a lot of things are going to keep on. There was this call for proposals that many of you knows about, which has a deadline in September, and that we will examine it in 1 month, in the coming months, where we distribute about 180K for 45 to 80 proposals. It depends on the years. So that's a small amount of money when you divide by the number of people involved, but it can help to visit each other, to create synergies, and to create some animation in the field. So that's one of the things that we try to help, is that the fields get animated and there is a lot of communication between us. So via this call, but there is also via the days, workshops, events that we organize as a council of the PNCG. And for instance, these days are organized by ourselves. When we look at the panorama of activities last year, we decided that there was room for making some days about galaxies, and we get together, and that the people working in the field of the evolution of galaxies have a chance to present themselves and present their work, especially young researchers. And it's more focused on galaxies because in cosmology, with especially the GDR cosmology, they also have other opportunities, so we try to equilibrate things like that. Via the SF2A also, where we always propose some workshops and one plenary speaker, and there is a newsletter. So if you don't know about the newsletter, you can still register. Probably the newsletter will change name soon because it will not be the news of PNCG anymore, but I guess something will keep on. So you can register and you can submit news about workshops you organize and resources, stuff like that. We also are, we also give some expertise on a frequent basis, like to INSU, when we are asked by the, sometimes before issuing a press release, the communication department of CNRS ask us if we believe this is good, interesting or not, sort of things, by the DAS, which is Délégué Adjoint Scientifique of INSU, so our boss, by CNES sometimes, and some, like there is maybe you know about this fellowship of a postdoctoral fellowship dedicated to James Webb. Well, of course, CNES asked us to have one person contribute to the evaluation, and for INOs and other committees. And of course, we contributed a lot to the prospectives that I will talk a bit more about in the next slide. You can cut me when I spoke too much. You can cut me if I speak too much. So a few words about this reform. So there is no more PNCG, I think you understood. And the PNAA has started. So right now, all the old programs which existed have become action thematic. The call for projects that we have been receiving in last September, with the deadline in September, has been basically redistributed to the action thematic. So before you made a proposal to us, now you have done it to the PNAA that give us back to us to evaluate. So it's exactly the same process will apply this year as it has applied in the previous years. The only difference is the animation. Everything that is related to animation is by status, not really in the domain of the PN, but in the domain of the CSAA, which stands for Commission des Spécialistes of Astronomy and Astrophysics. But still, the CSAA, which has been it has been renewed, and all the action thematic, we are part of it, and all the evaluation of the animation of the CSAA is coming back to the action thematic in the end. So again, we still do the same thing as before, but with a chain of things before. So these proposals, we are going to examine them soon, both the animation and the projects. From next year, we should not be a Programme National, but an action thematic. So apparently, I'm still in charge of it, but that should change. And the big difference is that we should be a smaller number. So right now, we are about 20 persons in the council of PNCG to discuss about the very wide topics that we address. And the typical size of the action thematic is expected to be 12. But I kind of negotiated that we could do if we are 16. And we are waiting for the reply, so we don't know exactly. But anyway, next year will be the start of this new form. The perimeter of the action thematic will be exactly the same as the PNCG for the first year. And eventually it will evolve if we discuss. Some people feel like Cosmologie with the GDR of EN2P3 is already kind of served in terms of animation, so maybe the action thematic should be splitted because we don't have exactly the same role now in Cosmology and Galaxies. Some people feel that there are fields which are really interconnected and that we cannot split. This will be the subject of discussions, and if you want to discuss about it, if you want to give your opinion to me or Benjamin or other people of the CS, you are welcome. About the news in the recent year, this year, there was a lot of debate. Some of you may have heard about the possible change of perimeter of the section of CNRS, which could have an impact for the job and careers and so on. So this has been cancelled. So we keep on with the same perimeters about the section as before. Of course, the question may be asked again in the future. But there is a group that has been nominated, that has been discussing at the prospective with the other institutes, because this is this change is very much. I mean, we don't do that anymore, but we're still discussing about how to work better between the two institutes. The big question is about EN2P3 and INSU. Then there was a prospective in Notrans. That's also some news I wanted to give to you, but I will not go into details, but you will have the slides, and there is a document online on the site of the prospectives. So there have been a lot of working groups. We have been asked as PNCG to give some input. For the ground, for instance, we listed a few means which seem to us priorities, in a sense, for our field. Those are the really P0. So that means priorities, subjects which are important and in which we have a big community that can support the science behind them. Okay, that was what was asked to us, and then the global group is going to work on it. There was a thematic group that has been defining some boxes like challenges, défis, fancy names for paving basically what people do in the different fields. And this is still in progress, in fact. Okay, so I'm going to pass that. I was saying there is a group about the relation between the institutes, so that has been, they are discussing, so that's a progress. The prospective of CNES I mentioned to you, so Mathieu is at the prospective of CNES. And same thing, we have been asked priorities, and so we said we absolutely need the ways to exploit the vast amount of data that comes from Euclid and James Webb right now, that Athena must be supported, because there was still some questions about is it accepted or not. It's not clear for everyone. And then for the future, we put forward Lightbird and the far-infrared probe like Prima, which actually was accepted by NASA for a phase A pre-study like yesterday or a few days ago. Okay, so for the prospective, I have many slides that I will not show you, but you can find them in the slides if we distribute them after, I don't know, and you can find them in the documents of the prospective on the website that I mentioned before. So basically they show a relation with the various other PNs, showing that we have a lot of interfaces, of course with the GDR cosmology. You have some information about our methods, which are mostly observations and some theory modelization, these sort of things. And about, we made a poll about to the people. Some people in the room replied. So many people didn't reply because it's mostly permanent people who replied, so I guess not the young ones. But it's a basis that we've used to put the priorities that I mentioned before. Okay, so I will thank here and thank you for being there and making the life of PNCG very interesting with this sort of meetings. Thank you.
Very much. Do you have any questions in the room? Thanks.
What is the rationale to change the PNCG? What is the rationale to change the PNCG to something similar, except the entropy?
Except what?
Except increasing the entropy?
So indeed, yeah, entropy is already increasing indeed. So the rationale is not very clear to us. It seems to be clear in the head of Nicolas Arnaud, which is the director of the INSU. And basically, the other branches of INSU are working with one program for the whole field. So they want to have the same type of things in the different fields. So in universe science, INSU, we were having many programs, and they just want one like the other big fields. And they think it will increase the visibility and could attract more partners to give money if you have like big priorities defined by a global program national. And we don't believe it will work that way. But there is one positive aspect, is that since we are much more interconnected with CSAA, we will have a more homogeneous way to proceed between the different programs. So that's one positive side that I saw, but that's the only one I saw so far. And I already seen a bit more work.
Any other questions? Then we can thank Samir again.
Thank you.
Very much. And now we welcome Matt Leonard from CRAN, who will give us an overview of the instrument project at CRAN.
That's me. Thanks for reminding me. Well, it's a pleasure to be here, and welcome to Lyon. I hope you enjoy your visit, even though we're going to have a tropical storm tomorrow. Now, coming from a country that's used to tropical storms, enjoy. So I'm here to present the instrumentation program of the CRAL. It's kind of a fool's errand because obviously there's a lot of engineers, about 20 of them, who do spectacular work for the CRAL. And like every institute in France, it's relatively dispersed, so it's kind of hard to corral. So I'd rather talk more about the sort of philosophy of it, because I think we're facing an inflection point where astronomical instruments are starting to become the scale of CERN experiments and things like that. And I don't think we're, as a community, well equipped to handle this. And I'll kind of point that out at the end without being too negative overall. Okay. Yeah, great. So I have an interesting way of thinking about it, because normally speaking, when you have somebody who comes up and says instrumentation plan, they tend to focus on these, what I believe is empty blue areas. And so these empty blue areas are usually your interfaces between R&D and simulations and instruments and this kind of stuff, and you fill it in with the usual fluff about how, we need simulations to justify instruments and planning, and then we need instruments to test simulations. But I really don't mean it like this. What I really mean it is each one of these is a kind of like a large instrument program in itself. And so in order to sort of corral all of these things together, you have to have a unified vision about what you want from all of these things, not only to work together, but you have to have a vision in themselves. And what's interesting is the one that usually gets left out of this is simulation work. So on instrumentation, I think we're well known for Muse, and so now we have a shopping list of things that we're working on currently, and probably in the future PCS will pop in here somewhere for the ELT. And then this is kind of our expertise. So this is the way I've split this slide up. And then on R&D, of course, we have TEMIS, LiveMirror, FlexiMirror, SELF, and ELF, and PRP Origins. And these are various technologies that are being developed within these kinds of expertise: metrology, high contrast, imaging and spectroscopy, nulling interferometry, advanced materials, and hybrid and additive manufacturing. So all of these things with our partners are being done within this R&D program of the CRAL. But more interesting to me in a way, which generally I don't see at presentations like this, is simulations. Because in fact, when you look at the amount of resources that are given across France for simulations and the amount of CPU time that we're using, the money and resources going into this is actually quite enormous. And it's typically unrecognized as this. So we contribute directly to ESO, for example, but who pays for the computer centers that we use? Sometimes it's like at ENSL, we have our own. And so there are these local ones, but there's also these national ones. And how are those resources counted? But if you sum up the amount of time and money it takes to run those things, and you include that in, this actually becomes quite a big instrumentation project in its own right. And in fact, what the tricky part about it is, and this is where vision is required, is that we're in this phase now where we don't know what the architecture of future computers are going to look like. They're going to be probably some kind of hybrid, CPU, GPU hybrid. Load balancing is a huge issue. How do you feed memory and retrieve it? How do you speed up that process of retrieval? How do you connect the CPUs or GPUs with their memory units to extract the most information from your simulations? And then their data volumes, because they use the term data, are enormous. So there's this back-end investment that goes in here, and it's often not recognized as such. But in fact, if you're in a lab, you want to integrate these things together in some common way so you don't get overloaded. My brain can only handle so much information. So you have to have a way of compartmentalizing it. And this is, in fact, a brain diagram for me, because this is exactly the way I look at it. So there's no trick to it. So unfortunately, I'm going to get into the part of the talk where it says shopping list, unfortunately. I apologize for that. I don't enjoy shopping list talks. They tend to go a little bit fast, but it is what it is. So here is literally the ELT on October 3rd. It looks like a real telescope. Okay? This is in our future towards the end of the 2020s. And it's enormous. You can see in this wide field image that, well, this is a crane, okay? So this is almost the size of like a football stadium, right? You could fit in, you know, some kind of monument in France inside the damn thing. So it's enormous. For us, we're building Harmony, and for an enormous instrument, or a telescope, you need an enormous instrument, because they scale to the diameter of the telescope by some obscene power, like d cubed or something like this. And so the volumes become enormous. So this is Harmony as it currently looks, because as I'll get to at the end, it's going to go through a change because of its complexity. But it's a consortia in France, in Britain, and in fact, Oxford's the PI Institute, Spain, and then there's a contribution from the University of Michigan. The total cost is 900 plus FTEs, which roughly translates into over 90 million euros in total. And then the hardware cost is about 35 million euros and climbing. So now you see what the problem is. You're talking about a project in total that's well over 100 million euros. To give you a perspective, a VLT I thought was 90 to 100 million euros each. Okay? So you're building an ELT, you're building a VLT to service the ELT. Okay, and Harmony's going to sit here like this. And at Crow, we're doing the IFU. So that's the integral field unit. That's where you slice it. We'll hear more about this from Roland when he talks about WST. It's the science software, instrument software, and we've been doing some IFS systems engineering and software system engineering. And we're going to give up about 130 FTEs. And unfortunately, this project is becoming multi-generational. So it started in the mid-2010s, and it's probably going to end somewhere in the mid-2030s. So it's a big undertaking. What it's going to be able to do is it currently has a visible channel at fairly low resolution, somewhere between about 2,500 and 4,000. And then it has various gratings to go through the near IR. And it has these 4 field of views likely to go down to 3 in some way, including a diffraction limited scale, 4 milliarc second, all the way up to sort of as large as you can do. Because what happens is, in order to get spaxels this large, as they're called for IFUs, you have to demagnify, which means your camera becomes very fast. And then there's a limit on the sizes of lenses you can actually put down and then freeze in cryogenic temperatures. So this is what ultimately limits the size of what you can do. So it's a workhorse instrument according to ESO, and I don't even know what that means actually, but what it translates into is about 130 modes. Now, if any of you have actually used VLT instruments, there's no way you're going to have 130 modes at the telescope. But anyway, so the complexity adds risks, and many mechanisms need prototyping and verification, and the science is enormous with this. We're also part of Foremost. So Foremost should be going to the telescope probably next year. The problem with Foremost is we have to recommission the telescope because it's the Vista telescope, which is a 4-meter near Paranal. And basically what we did is we cut the top end off, and the top end is going to be replaced by a multi-object spectrometer. So Foremost is quite nice. It has 1,600 fibers at low resolution, about 800 fibers that can be run in parallel at higher resolution, R2000 and R around 5,000. It covers the full optical, and then it has this high resolution mode, which covers 3 separate bands. It has a large field of view. It's about 2.5 degrees, so it's quite nice. So the status currently is PA1, so that's Preliminary Acceptance Europe, Part 1, was passed a couple of weeks ago. And then PAA2, which is like the rest of it. So why is PAA1? Because they need to put that top end on the telescope to commission it, because it has the guide CCDs built in. So this has to go. So it's going to be shipped to Paranal. And of course, as you might imagine, when you have a high multiplex spectrometer, you can do a lot of science with it. And it's really a survey instrument. So it's going to run on Sky for 5 years for public surveys in parallel with PI-led surveys. So it's quite ambitious to follow all the data and do it. And it's a relatively large consortia for obvious reasons. And this is it in a nutshell. It's at the top of the telescope, and it's a beast in itself. This is where the secondary used to be, and is now filled with Foremost. And and this is various things. So I won't go through the whole thing, but it's complicated. Wide field corrector. The electronics have to be hidden somewhere. And this is the part we built. It's the low resolution spectrographs, which sits down here, and they're enormous. This is what they looked like in the lab. This is just one of them, because it's a 3-channel spectrograph, and I forget which order it goes in, but I believe this is the blue, the green, and the red channels, like this. And then these are some of our engineers discussing it for a picture. So anyway, so what we built is this, and we built 2 of them. They're duplicates, and they're enormous. So it's 812 fibers for that. In total, there's 2,500 fiber probes themselves. And what they are is, I didn't show the film, but the film's kind of cool. So what they are is these little magnetic steered ends, and the fibers do this, and they jiggle back and forth. And that's how you find all your targets. And so it's a field of fibers, and they just move like this. Oh, wow. Okay. That went by very quickly. Right, and you can see that it's all moderate resolution. So here's Blue Muse. So Blue Muse is quite simple, actually. I'll get onto that in a second. But what I want to show is, because Roland Bacon is in the audience and he loves this plot. So this is number of publications and then year past when they become scientifically active. And this is Muse. So clearly the community wants a Blue Muse. So we're building a Blue Muse. So it's optimized in the blue from 3,500 to 5,800 nanometers, and it's about R3500. It's designed to have very high throughput and to be simple, point and shoot. And this is how simple it is. That's all I have to say. It's a consortia currently spread around Europe, and here are the institutes. And then here's the schedule. So it looks like around 2032. And Blue Muse is simply not a blue optimized Muse. We're spending a lot of time to learn lessons from Muse to make it a Blue Muse Plus. So don't think of it as a duplicate. It's really an improved version of Muse, which is already the most successful instrument at Paranal. Okay, high performance computing. So clearly, we've been quite successful in pushing this forward. So in Crow, we've actually done a lot of work historically since 2012. Look at the number of hours. These are mega hours of CPUs on various platforms. And we've also invested in our own computing facility. We're part of the Guinea group. So in there, the development is for Diablo. And now as we move to the new kinds of computers, it's going to be exascale. Did I get this right? Sorry, you were talking.
I was talking about the fryers, because there were investment from fryers to cool down the computers.
Ah, sorry. Anyway, so what you're looking for here is you're looking for scalability. and time to solution. So this is going to be the inverse of a plot I'm going to show. So actually you can see what happens is with this new design, so this is Ramsey, so this is kind of like the workhorse code that we are using at CRAL in general. There are other codes. And what you can see is as you go to these other ones, the time to the same solution is actually shorter. So it means you have an improvement and the scalability looks a bit better. And then finally, now this is a slide I got from, can't quite see it, but it's Timothée David Clarice. And so this is Shamrock. So this is an internal development. And what he's done is he's written a very flexible code in C++, which can do smooth particle hydrodynamics, or it can do adaptive mass refinement. You can pick and choose. It's based on SYCL and MPI. So that means it's scalable to heterogeneous systems. So it has an underlying floor to it that actually serves the command so you don't have to worry about it. It has Python to run scripts, and there's more than just run scripts because it means you can interact with the code through Python, and since a lot of people can program in Python, even though Python's not very efficient, it can call out information that the code will do and bring it out. So that's the advantage of it. And so you can see that, in fact, you know, it's actually quite an efficient code. They're up to over 9 billion particles. And here you can see the particle seconds as you go in various GPUs and how many particles and how it scales with the number of GPUs. So the scalability is quite nice. So since I'm out of time, my message is essentially, look, ELT instruments are more costly, more complex, and physically just larger. I mean, Harmony is enormous. It's like a small apartment building. You literally need stairs to climb the Dewar. So it's crazy how big it is. And so de-risking projects is quite important. So yes, you might want it to do every science case known to humankind, but that carries a risk with it. So when you say workhorse instrument, be careful what you wish for because they become quite complicated. The next generation of code for exascale computers has to be supported for the technical challenge that it is. It's not the same as it used to be. You need a generation of people that can be adaptable because computer technology is changing very rapidly, and it's not driven by astrophysics. It's driven by other things like AI. And so we have to be able to adapt, and this requires significant resources, and it's no less important than VLT or ELT instruments in themselves. And I think in the ELT instrument, the VLT will take on new importance, not less, because it's going to be hard to get time on ELT. So a lot of the science that's going to come out of ESO is going to be based on ELT instruments, and they have to be efficient and capable, and hopefully not very expensive. And in France, like other countries, we need to set stronger scientific priorities. The scale of what we do in astrophysics is enormous now, and if you don't set hard priorities, I'm not sure how we're going to participate at a significant level. If you like being 5% partners in every project known to humankind, be my guest. That's not my choice generally. I would rather be a more significant partner in fewer projects and play a stronger role in them, but it's a choice. And the way we're going, you know, we can no longer be part of every instrument or every space project. I don't see how this is possible. Thank you. It's a flashcard feed.
I was wondering about the resources, like the numerical resources to build out the codes, because you also need the supercomputers. Is it something that is, are they European-based or European-founded supercomputers, or is it money that is also something that you need to look for?
It's actually all of those things, because there was Eurospace up there. Euro HPC Space was part of a project that Benoit Camerson is part of. It's not here. And so there is European resources for this, but as far as the hardware goes, that's not driven by us. What it's going to be driven by actually is the total electricity you need. So one of the things that is happening is they're actually capping the amount of electricity a computer center can use, and they want you to build something underneath that cap, which I think is a good idea. Because it turns out in the US, it's been estimated by about 2030, about 10% of all the electricity will be consumed by AI. So we're gonna have to do something. This is not sustainable.
Thank you very much.
Thank you.
Thank you. Maybe one last quick question?
Yes.
So about the computer architecture and how it's evolved and we need to adapt to it, is this Shamrock code something that you mentioned because it's trying to take this into consideration and anticipate
Yeah.
future computer architecture changes?
Yeah, because it has, what is it? It's Cocos underneath it, right?
SQL.
Sico.
Yeah.
That's right, Sickle is underneath it.
Yes,
It's Diablo that has Coco.
exactly.
Okay, so what happens is various institutes like Sandia National Labs are writing these things that should be architecture independent.
Okay.
And you build it on top of that. So Sickle's like that too. Thanks.
Thank you very much.
Thank you.
And now we have Jean-Jacques Lyon, who will talk to us about the first Euclid science results with the early release observation.
Bonjour tout le monde. Hi everyone. I'll stick around so that people on Zoom can hear us, right? Close to the microphone.
Sound is pretty good.
Yeah.
Wander around.
Okay. So it is my pleasure to present some of the early results from Euclid. And I want to say here first, before we move on to the actual details, I assume the slides will be distributed so people can look at them more closely, because it's going to go very fast. It's going to be my shortest debate talk ever. And you know, I'm an astronomer, and my job as an astronomer is to enable science and often, you know, serve the others. And so, luckily in the audience we have Maëlie, Timur, and Louis, who will be talking about some of the hero science. And so that's why I'll be, you know, going quite fast. And actually, I want to show you some pretty pictures. So, as you know, Euclid was motivated to study the dark universe, and so dark energy, dark matter, and such a thing. So really cosmology-driven mission built by ESA. And so that drove the design of the spacecraft and its instruments. And so essentially we have a 1.2 meter aperture in space with panoramic cameras, both in optical and infrared. And we're also doing spectroscopy at low resolution, about AR400. And we're sitting at L2, and the main mission is going to last for 6 years, but we now know the spacecraft, with all the successful launch and all that, is going to last for 12 years. So it means Euclid is going to be in the community for quite a while. It was motivated by a science case. The science case was pushed forward by this scientific corporation called Euclid Consortium, which is currently about 2,000 members. And mostly it's people who are interested in astrophysics, and there's some cosmologists who actually drive the thing, but really it's because Euclid catches everything in the way of looking at these 2 billion galaxies we're after for the cosmology. You get to see all the range of science. And so that's why the hero I'm going to tell you now about are coming up. So knowing that the cosmology results would take time, ESA was kind of worried 2 years ago about, you know, letting the world take notice of this new magnificent telescope. And so they approached me because the pipeline, the infrastructure that is set forward for the consortium is really not designed to produce pretty pictures, which was the very first motivation of the early release observations. And then later on, it turned out that the infrastructure I had to come up with also had to serve the first science. And so that's what you're seeing here. And so, of course, because, you know, we have this large extended object, we wanted to have pretty maybe these big objects in the field of view, not those billions of galaxies, which are like covering a few arc seconds, not very exciting as a sight. The problem is when data arrive from space, it's very new for me coming from the ground, you have space weather. And so, for example, the optical mosaic of CCDs, you get a lot of cosmic rays, just one of the signature. In the infrared, we have detectors which have their own behaviors. You know, it's a very complex technology, and it has persistence. So it remembers what it's been doing up to days before that. And so here, because we do spectroscopy, all the imaging is literally scratched by the memory of the previous spectroscopy. So you have to deal with all these aspects if you want to build a data set worthy of science publication. And so that's why there's a lot of effort that went into building a pipeline, essentially, that has a lot of legacy from all the stuff I've done over the decades with Canada, France, Hawaii telescopes, where I also work with the same type of detectors, the same type of surveys, same type of objects. So it was like an easy fit for me. The difficulty in all that was to do it quick, because, you know, starting fresh once we launched, I had like only a few months to deliver the first images, and essentially a few months to work for the group of scientists to come up with the first papers in the list. And so, because the early release observations were designed to wow the world, to impress people, and it did work. The images have been going around and been seen quite a few people. We were not constrained by what drives the main survey, where you have to stick to the galactic caps, right? Because you're looking at the distant universe. Here we decided, okay, well, we're always pointing our back to the sun to keep thermal stability. But as doing so you at any time of the day, you can only look at a stripe around you because you can rotate on your axis. But that limits kind of what you can see in the sky at any time. Still, we knew exactly what would be in the sky in October, November, December of 2023, and that gave us a bit of a choice after calling for ideas from the community, essentially scientists from the Euclid Consortium, who saw an opportunity there outside a bit of the system to have more like PI projects with Euclid. And so that's what we did. And here you see the range of objects, and the narrative we picked was to explore the increasing distance from our local neighborhood in our own galaxy out to a fairly distant universe, with a backstory being the field galaxies. The main target that Euclid will be really focused on for the next 6 years for the cosmology will be those field galaxies. So that's why they appear. And if you followed the press release we've done over the past few months or year now, you can see when I did cutouts for ESA, I always paid attention that, oh yeah, we can see those background galaxies. They're always someplace in those fields. And so, one of the topic was to study star formation region, and in particular looking for free floating planets. So that's Messier 78, and we're going to play a little game here for the 10 images that you have all access to this on high resolution, high quality on the ESA site if you want to go have a closer look for yourself. The yellow box is essentially, I'm sure that's a 2K, it's not a 4K projector, it's a 2K projector. So even what I'm showing here, even though it's 1.4% in resolution of what Euclid captures, with the optical channel. The infrared channel is a bit lower, but with the optical channel, you could actually fit 4 screens like that. Okay, so this is the full field of view of Euclid, and this is 1.5%, and you can still see a lot of information. So what's powerful, what's potent with Euclid, because we had so little time to cover 1/3 of the whole sky for the mission, a lot of choices had to be made technically. And one of them was to really drive the instruments into almost critically sampled system. And so when you look at the images from Euclid, you have information on every single pixel. It's not this, PSF is critically sampled, so every pixel counts. So the 610 megapixel from Euclid on the VIS do carry information, and we'll see it better with the galaxies. Also Nebula, of course, that we picked it because we knew it would work, and it did work. That's the one that drove one of the exposure we get from billions of people around the world. It's a classic view, except this time we have the H band. We have optical. We have 1 foot in the optical and 3 feet. We have 4 feet. We have 4 bands. And for the RGB, I use H band, the V band, so it gives you a nice range of colors. And middle, I pick the Y band around 1 micron. So you have quite a range there. So you're going to catch different physical phenomena in your image. And so the H band reflects the dust scattering, and so the objects take a different structure. Here, when you zoom in, maybe you've seen it with the M78, but you see like the H alpha emission, which is now in the blue filter because it's captured by the optical band of Euclid, and you start seeing field galaxies behind the horse head in a high resolution, as a matter of fact. And so here the scientific motivation was hunting down some free-floating planets. And the rationale here is you can go down to 4 Jupiter masses. They're still warm enough that you can spot them in infrared. The lesson learned here is that proper motion is really critical to complement Euclid. Euclid probably by itself cannot really deliver the whole science. And so the team by Eduardo Martin is working hard on that. So they have a few things. Then we move out to the halo of our galaxy. We picked up this program by Davide Massari about 2 globular clusters. And here you see the beautiful view. It's really one pointing, you're almost pointing into the plane of the galaxy, so very rich stellar field. Then when you go into the periphery of the cluster, you still can spot all these field galaxies that are lurking behind. And so here, again, these Euro programs, they were selected because scientifically they were worthy of illustrating the amazing capabilities of the telescope. It's so new in terms of what it can do that any way it looks, right? It's a bit like Muse, and you have something that is so new that is going to change the way you perceive what you're observing. So Euclid has some of that. And that's kind of what the idea, like, well, what happens if you're the first to look at the global cluster with Euclid, for example. So here Davide was looking at the shape as the outer. We're able to, of course, resolve stars down to faint magnitudes and to look at possible impact of the variation of shapes around on the outskirts, tracing the dynamic influence of the galaxy on these clusters, and the signs of it. So that's the first result. Moving out into the local group, now we have one of the local group galaxies, NG6822. Now you know the trick. You will see maybe some field galaxies behind, but what's interesting is a star formation region, and you see the color is again the result of H-band scattering and the H-alpha emission that give you purple. So there's something unique in the colors that you get from Euclid, from this sort of separation in different bands. IC342 is a hidden galaxy. Not so much when we look at it with Euclid, and then here you resolve most of the stars. It's like arguably one of the sharpest portraits of a galaxy in one shot, right? And here you see the grain you see on the screen. You get a bit of that. It's you see the background galaxies, but the grain that is really coming from the resolved population of stars in the galaxy. A bit further out, we have 6744. And this one, again, like I was showing, I was giving a public lecture last week, and galaxies are mostly made of vacuum. You can really see through this, translucid, as you can see with this galaxy on the right. So again, take a look at either those slides or on the ESA side, you get a good sight of what these images are about. So the PI here, Leslie Hunt, was illustrating the capabilities of Euclid with complementarity with multi-wavelengths, as we know it, the stellar population, all this stuff you can do once you have the power of resolution of such scale. Moving out further out, this is looking at groups of galaxies and local clusters. So PI was Ariane Manson, and so we captured this, in particular, this Dorado group. Again, 1.5%, and you get to see this, you resolve the brightest elements, the brightest stars from dwarf galaxies around this group. And then the science was motivated by tracking down, and Timur will be telling us more about this, tracking down globular clusters that you can not resolve, but you can really have enough information in terms of the point-spread function that can separate them from stars. Okay. And then we had Perseus, and so the PI of this one, with this one we're so ambitious, so you see the resolution, we did 3 papers, and we doubled the number of known dwarfs in the cluster, from 600 to 1200. With that in mind, we decided, we're going to make a nice luminosity function, and so that was the main goal of this paper, and with a flattening luminosity function on the Fein regime. And then we also had a third paper on the intracluster light. And Euclid is going to be great, really, because it's so powerful with low surface brightness universe that we identified this large halo of stars. We found also 70,000 vagabond, I like to say here, globular clusters that were into intergalactic space, and so exciting result from Perseus. Then to conclude, we had more distant clusters, and the idea there was to illustrate lensing, which is more closer to the cosmology goals of Euclid, although the regime is completely different from what you do for cosmic shear, for the dark energy. It still was a nice illustration of what Euclid can do. And then the team from Akim really came up with 2 papers, and also this one is about the dropout sign, which is going to be a massive impact of Euclid because we have such a nice sample. And just 2 fields, I think, for this Euro, we found 30 extremely rare objects, very red, up to redshifts of 6 or 8. And so now this was the Euro were I think 10 square degrees, but now we've acquired more than 1,000 square degrees, so you get the idea of how big the sample is going to be. And so everything is on the ESA site. You can find all these papers. So enjoy your reading if you want. Thank you.
Questions for you,
You mentioned at the end the low surface brightness and the intracluster lights and these sort of things. So this is with the hero where you did the pipeline really designated for that,
Yes.
right? So what's the prospect for the future data? Do we have the same type of possibilities or?
Yeah, so these darn cosmologists, right? They don't care about it, so they kill it. They kill the signal. But we found a way with what ESA is setting up called data labs. And with data labs, we'll be able to branch off from the official pipeline and be able to kind of reconstruct the signal up to a certain scale. Not all of them. We can, because there's some elements you do in the processing that are going to affect the signal up to a certain element. So I think the way we're looking at it, we'll be able to do mostly stuff up to 10 arc minutes, 5 arc minutes, which is mostly the volume of universe we're going to explore is right there. And now I take this opportunity to take a look at what's coming out in a week or so, 2 weeks from now from ESA. We have a new press release coming up. And this one, I explore more for what could be seen on the larger scale. And so hopefully seeing how Euclid is very, very good at exploring the scales from, at the sub-arc second scale up to very, very large object, maybe change the mentality. We'll see.
It was in the background first.
Jean-Charles, thanks for this talk. You spoke about spectroscopy in the treatment of the data. Did you manage to extract something yet outside of the spectroscopy in terms of science?
No, I think we were, lack of time, we were all very pressed during those first papers back in the spring. Also, the spectroscopy is very complex because of all the persistence aspect and the SGS, which is a sine drone segment. All the people part of the consortium were working hard on that. So I can see how difficult this is, and so I'm good at doing imaging, but I know nothing about spectroscopy. So I bailed out from that one, saying I can't do this. And hopefully, what the hope is that for the ERO, because we have spectra for all these fields, is that the SGS will be processing them in time for DR1. So hold tight, but it's going to come at some point.
Maybe you had a very quick question?
Oh, I'm not so sure it's very quick. Maybe we can talk about this at coffee, but it's very impressive data, I have to say. I know it's early in the project, but what one thing have you learned that you wish you could change? Again, maybe it's not a short answer. We can talk about that.
Well,
later.
it was interesting where Euclid has some of issues if you follow the news, and so you would like to go back and say, well, maybe we could fix that. It was like there was some elements where, okay, as one example, for example, spectroscopy, eventually the solution found is better than the initial plan, but we're supposed to have rotated grism. Okay? We're not slate spectroscopy doing grism, so we're getting a spectra of everything. So everything is happily overlapping every signal. So we had this rotation scheme. And then once we did everything integrated, everything and started testing the system, realized that one of the grism was rotated 180 degrees.
Right.
And what happened is, some designers pick like axes like this, and the mechanic guys take it like this, and the optical guys took it like this. And so, sure enough, it happened. And so we had to find so maybe better communication across the board. Maybe that would be one.
Thank you very much. Thank you. And now we welcome Rafaela Lo from LAM, who will talk to us about the history of galaxy migration over the stellar mass.
Yes. So, hello everyone. I'm really glad to be here to present some of my work, some recent work, using the Cosmos web data, where the idea will be, in fact, to make an observational description of how galaxies move through the stellar mass and the star formation rate plane, using the reconstructed star formation histories using a non-parametric SFH approach. And this work, in fact, made part of a preamble on the construction of the full catalog of physical parameters and photometry for the Cosmos Web survey. So for all my work, I am using the SCD15 code SIGAL, and here I am showing just the basic recipe that I'm using, where I will mix the BCO3 models, the non-parametric star formation history. I will apply some templates in nebular emission for lines and continuum, some attenuation law, dust emission, and the whole Bayesian-like analysis to get the star formation rates, the stellar masses, and as well the star formation history in a non-parametric approach. So the non-parametric approach for the star formation history is just a discretization of the star formation history, where we will fix the number of beams, the size of the first beam, and the number of SFH models that we will use in our Bayesian-like analysis. And the only free parameter will be the duration or the size of the star formation history, and the whole will have some priors that will weights against some sharp transitions between two different beams of the star formation history. So another parameter that we have included in this non-parametric star formation history for SIGAL is the computation of two parameters that will help us to track the movement of a galaxy through the plane, given the direction and the displacement or the velocity of the galaxy through the plane. And that is what is really interesting as well, is that we will be able to distinguish the recent trends of the star formation history in a given interval of time, so we can compute this parameter or this vector in a given interval of time. So in order to check if we can recover these parameters and the general physical parameters that we will use in this study, the idea was to apply SIGAL over the horizon AGN simulation and use the fact that for this simulation we have the star formation histories in high resolution, and we will take in account for galaxies between redshift 0 and 4. We have some basic physical properties as the gas cooling, feedback from AGN, from the supernova, and also the fact that we have the GWST virtual photometry. So here I'm just showing the comparison between the real simulated parameters, for instance, for the star formation rate, and the parameters found by SIGAL, and the star formation rate, the stellar mass, and the direction of the galaxy through the plane, as well as the velocity, in order to check if we can recover well the parameters in order to make some statistic with this data. So, as you know, the Cosmos Web is a survey, a legacy survey that have more than 0.5 square degrees. On the Cosmos Web version of this survey, we have more than 700,000 galaxies, and we will have, and we have in fact, 4 NIRCam points and 1 grid point. And for this particular work, I will select only galaxies with redshift 0 and 4, and I will use the legacy of all the photometry that we have from the far UV until the mid-infrared now with the NIRCam and MIDI observations. So here I'm just showing the tile analysis at low redshift, where I am color coding the plane in the direction of the movement of galaxies through the plane in a time, in a look-back time of 1 gigayear. And just the thing that we can retain here is the fact that for galaxies that where we found normally in the starburst region, we will have a recent increase in the star formation history, while for galaxies in the passive region, we will have a decrease in the recent history of the galaxy. But more interested could be to check on the dispersion of the movement where we will have that for regions, marginal regions, as the stardust region or the passive regions, we will have a high homogeneous star formation history, while for, in particular, at this bin of redshift, we will have that galaxies in the main sequence will have a more degree of variety in terms of the recent history of the galaxies. Then we can also check, for instance, on the speed, the velocity, or the displacement of galaxies. And what we found, in fact, is that galaxies around the main sequence will move really slow, while the marginal populations will move with a high velocity or a big displacement. So here I am showing the plane through different bins of redshifts. We have tested for different models to check which model fits the best to our observation. And what we found, in fact, is that the Schreiber 2050 model fit the best through the all distribution of redshift of our observations. Then, if we apply this color code on the direction of the movement of the galaxies in the last 700 years, we can see how we can see, in fact, this nice rainbow distribution of the movement of galaxies that go up to redshift 4 with some maybe some dispersion in different regions. But it's really nice to see how these regions will share, in fact, the same kind of recent history in terms of the star formation rates. So what we can do at this point is try to reconstruct, for instance, the position of a galaxy in the plane. So here I'm showing the distance to the main sequence. We have selected some galaxies in the passive region, and we have tried to reconstruct the position of the galaxies in a previous bin of redshift. So here we have the observed redshift, and here the reconstructed redshift. So what is really interesting of this approach is that the fact that we can now have a visual image of how galaxies will move through the plane, but at the same time we can, for instance, quantify the fraction of progenitors in function of redshift or cosmic time. So here, for instance, we can see that at high redshift we have a population of the passive region that is dominated by galaxies that come from the so-called Green Valley, while at the whole distribution of redshift, we will see that the progenitors of the passive region are more or less homogeneous for galaxies that come from the main sequence or the passive region as well. So this is some open questions and some future explorations that I think that will be natural to continue with this kind of analysis, is to check the morphology in function of the variety of star formation histories in a given region, or to check, for instance, the diversity in the star formation history in function of the agent component, in particular for the high mass end of the plane, or even to check how the migration vector and the quenching timescales could change in function of the local environment. So I think that's all. And if you have some questions, please.
Thank you very much. Do you have any questions? I have several. Oh, maybe.
I can ask one. Can you go back to your diagram with the arrows all pointing down? That's fine, that's fine. So you don't actually have a time scale built on that plot?
No, but these are the movements through the last 700. No, sorry, is the time scale that we use to compute each arrow is the time scale from the redshift being here is ZE and ZP.
Yeah, so it's the delta T between those
Yes.
two redshifts.
It's the cosmic time redshift.
That's about a gig a year?
It depends. At low redshift, it's about a gigayear.
Oh, I see, because they're all different. Yeah, all right, right, sorry.
Yeah. Each panel is for a different bin of redshift.
So am I correct then, as you go to higher redshift, there's a bit of acceleration in how fast they move?
Mm-hmm. Yeah,
Okay.
but yes, in fact, we can see that in this diagram, where we will see the velocity of, here's the velocity of the galaxy through the plane. But here is not between two bins of redshift, it's just computed in the last 700 gigayears.
Okay, thank you.
Yes.
Thank you for this very interesting talk. I have a question about the robustness of the SFH that you derived. I was wondering, like, from how many magnitudes do you, I mean, there's always this issue of how much information can you take up from only like a few tens of magnitudes, like, how does it, like, can you comment on that? And also about the time scale that you choose. I'm not sure if I remember correctly, but it was like beams of logarithmic time, so like for bursty star formation, which is very much discussed for the early star formation thing, like how well do you model bursty star formation with these beams?
So the second question here in particular, we use the priors, the continuity burst priors, to take into account like the burstiness of galaxies, but at the same time to not to go too far when we compute the star formation history. The other point, I think, is between the robustness of the star formation history that we recover. So that's the work that we do by applying CGAL to the simulation, to the horizon imaging simulation, and we check at which point our star formation histories could be well recovered when we compare to the simulated ones. So the whole time scales that we use here are the time scales at which we can recover the star formation history at least in the simulation. This is our only guess, taking into account that the simulation maybe could reproduce the universe well or
Okay, thank you.
Any last question? Then I would like to ask you about the treatment of the feedback, because the recipe for the feedback can vary a lot between different simulations. So do you think of applying your method but to another simulation, except if the results are similar?
I mean, in principle, if we have access to the star formation histories, we can apply the method just to check if we can recover the measures. Yeah.
Thank you very much.
Thank you.
Well, we can try again. And now we have Mathieu Berthemin from NAM, who will talk to us about the Nickel 2 cosmological data system.
Yeah, it's better if you share on Zoom.
That's what I'm doing. Does it work?
I keep it.
Okay. I will go through the Wi-Fi.
You have a room.
No, it just was. Okay.
The sound is better.
Okay, so I don't need to.
Yeah, we can record it.
So, hello everyone. So I have the pleasure to present you the results, and Stefano will give a second talk about the same survey, about the Nika 2 Cosmological Legacy survey, which had a huge support the previous year thanks to the PNCG. So for this sort of project scale, PNCG is in fact a super good format. When you have like staff, but you just need to have a bit of funding to travel and stuff, it's perfect. So PNCG is super useful, thank you. So what was the goal of this survey? The goal was to probe the dusty star formation in the high redshift universe. So here you have the star formation rate density as a function of redshift. In blue, you have what we call the unobscured star formation. It's essentially the star formation you can probe from the bright OB stars that you form and live a very short amount of time. But most of the light from the young, freshly formed stars basically is absorbed by dust and re-emitted, if it's in a darker color, in the far infrared, typically as dust emission around 100 micron rest frame. So we know very well what happened to redshift, let's say 3, 4. When we started the project, 4 was already a big border. Now with ALMA we start to have constraints, but basically what's going on really between 4 and 7 was really unclear. And we think that at certain moments the star formation galaxies need to start to be dust-free, because you need to form stars to have metals and then to have dust. So one of the big questions is to know basically when the unobscured star formation cross basically the obscure star formation. And it's really important to obtain this obscure star formation if you want to study the most massive galaxies, because as it has been shown by ALMA, when you go to high stellar mass, the obscure star formation becomes really important and can reach a quantity which are really high, can be 80% or more. And in this case, you can miss a lot of the star formation history, and especially the assembly of the most massive galaxies, if you don't have access to that. So to study that, we use the NICA 2 camera, which is a camera based on a new generation of detector called KIDS, which we installed on the IRM 30-meter telescope in Pico Veleta. And it observes simultaneously at 1.2 millimeter and 2 millimeter, which is very specific to this instrument, with an angular resolution that you will see it's a problem, but it's also what you can do in the millimeter because of diffraction. It's 12 and 18 arc seconds. So the survey was following 2 fields. So initially when we designed this program, we chose to go very deep in a field in the north called Goods North, which has extremely good ancillary data, and another wider field in the Cosmos area, which has also very good data, but over a wider area, which allow basically to complement. This field is to study very faint objects, but over a small volume, and Cosmos is more to make statistics on big volume. So it has been led by Guylaine Lagache, Alexandre Belen, and Nicolas Pontieux. Then we had a lot of analysis to do, and it's not so easy to reduce this data, and Stefano also knows about that. But we had also to understand all the observational effects. It's not so easy to use millimeter data from the ground. You have the atmospheres, the telescope resolution. So to understand all of this, we had to basically develop a simulation. So we start from a model we developed, a symmetrical simulated model of galaxy evolution in the long wavelengths. And then we have to apply various things. So first thing we do is we degrade to the resolution of NICA 2 to understand how basically when you degrade the resolution, objects tend to blend, and basically you have already some biases when you interpret your data, so what we call a blob catalog. And then we basically use true noise, combine it with this simulation to create artificial observing timeline on each detector to create basically simulated catalogs produced exactly with the same map making and then source extractions and the real data. So from that we can have both the impact of the resolution, so basically what's the difference between the blob we see and the true galaxy in the sky, and there is a small bias because the blob can contain several galaxies. And then we can also, through this end-to-end simulation, perform, I don't know why we can remove that, perform this big simulation, so we can also complete completeness, purity, and also flux boosting effect. So the idea is here you have galaxies, and here the line is roughly the resolution of NICA 2, and in a blob you can have several galaxies. So sometimes you have just one bright galaxy and very faint one around, so it's not a problem. But sometimes you have 2 companions which are roughly at the same brightness, and that's another game. So in the end, we obtain something like 400 detection in total over the 2 fields. So it can seem small, but it's not so easy to build big sample in the millimeter, especially when you aim to the very IC. So after first thing we looked at is what we call the number counts. Essentially, it's a flux distribution of the sources you can see in these surveys. And since we had end-to-end simulation, we could really interpret what we see. So here, it's the number of objects as a function of the flux you detect. So the dashed line is what we have in our simulation if we just look at the galaxy in the simulation. And in fact, if we apply the full observational process, we will get the blue line here, which take into account some effect on the instrument, but also the fact like you're not observing galaxies, you're observing basically blobs. And then when we compare these blobs with the true data, you have an excellent agreement. Every data point is agreeing at 1 sigma with your data. So that's one thing is when you see basically sub-millimeter catalog, never consider that a single galaxy. In fact, there are some effects. The second thing is basically to compare with models and other data. And one interesting thing here you can see is our data points are in orange and red. The field symbol are basically observed with single dish telescopes. So basically, it's big antenna, but not that big, so your resolution is worse than 10 arcseconds. And the open symbol is observed with interferometer. And in fact, we agree very well with other observation on single dish with low resolution, but interferometer are much higher resolution, they pick galaxies, and it agrees with our correction of the number counts to go from blobs to galaxies. So that's something which was not done always properly in the past, but now we have developed method, and it's presented in this paper of Long Jibing, how we can interpret it in a consistent way to avoid this pitfall of the resolution. So we also compared with models, so after correcting to get galaxy counts, you can see that there are some small tensions somewhere, but it's overall working very well with recent models, so no big surprise. Would have liked some surprise, even if there are some models have a slight deficit at high flux, but overall that tend to confirm the model. So we didn't learn like new thing, new type of galaxies, but at least we confirm that what we have predicted was solid, which is already an interesting measurement. Then we looked, try to guess, instead of looking at objects we can detect, we try to see the impact of objects which are just below the detection threshold, because since we have a bad resolution, if you go sufficiently deep with your data, at some point you have always galaxies everywhere, in every beam, and this tend to create some fluctuation. So the idea is you mask your detected sources, and then you try to see if you have some residuals or in standard deviation of your map, which are above what you would expect from pure noise. So that has been done in a work by Nicolas Pontieux. So here you have the variance in your data as a function of the integration time. So it's decreased essentially with the time. And you can see in the solid line is what you expect from pure noise. In fact, we have a strong deviation which starts to appear here, which suggests we are approaching what we call the confusion limit. The moment you're not limited by the instrumental noise, but the fact just you have so many galaxies which tend to blend into your low angular resolution, and it's a sort of strong limit. And in fact, the level of this confusion is interesting also to learn about galaxies. So we measured it. First, we compared with our simulation, and in fact, we found a very good agreement. It's in the 1 sigma range. So that's really good news. That means even the source we don't detect have good properties compared to models. So that's, and in fact, we can check roughly which regime it's probe. So here you have as a function of the flux, so your bright flux and faint flux. Here's the contribution to the background. So essentially the contribution to star formation rate density. It tends to peak here, and the flux cut of your survey, the sources which are detected and masked, are here. So essentially, the sources which are just below your detection limit are the one which contributes the most to the star formation budget. But the fluctuation is different. It's really rise sharply, and then the source here could contribute, but since we have masked them, they don't contribute. So the bulk of the contribution is here, essentially. So we are essentially probing the population which contributes the most to the star formation, and we are roughly half a dex below the detection limit. And the fact that we find the right number suggests that we have correctly modeled this population, except if you have a very weird, faint, ultra-abundant dusty population, which is really unlikely physically. It's tend to confirm that what we have forecasted in the past is at least reasonable. So after we started to focus more on the colors and redshift of the source we detect at 2 mm, which are a bit harder to probe, and there are less surveys at this wavelength. So we found basically that the colors are really consistent. So we had some correction if there are galaxies, you look at blobs and end-to-end, but we made full simulation to integrate all the effect, and we have a very nice agreement. We also looked at the redshift distribution. We have found an overdensity in one beam, which is under study, but overall, if you remove this very strong overdensity, you have a good agreement. And then we started to look basically if you could use the color between the 2 mm and 1 mm as a tracer of redshift. Some people have claimed that maybe the 2 mm is perfect to find very RZ. It looks like that. That's the redshift. that's your ratio, and that's what you expect from models. So indeed you have a small deviation, and that's the error bar you have on your source, because you have flux deboosting, you have error on the two bands, and blah blah blah. So you see it's really hard. It's slightly better if you use 850, but it's remained really hard. So I was advocating, it was a bad idea to do that long time ago, but at some point that was cool, because now we can say it's probably not the best plan, but at least we know why now. And in fact, since we have a model which seems to be good at predicting what we have observed, we also looked at the performance of 2 mm survey compared to 1 mm, which are more popular, but some people advocate 2 mm is cool. So the big argument is if you go to longer wavelengths, you will see higher redshift. That's true. The average redshift is slightly higher, but don't forget that the emission of dust decreases really quickly when you go to longer wavelengths, because you're in a Rayleigh-Jean tail almost at all redshift, except above 10, but well, not so many objects at 10. So essentially here you have the dark blue is 1 mm selection, and the 2 mm selection you could get with a similar depth with NICA 2 is here. So essentially you don't gain anything at high redshift, but you lose object at low Z. And since we need any way to make a source identification with higher resolution observation, and then identify things through basically optical survey to get redshift, some follow-up, it's probably this source we would manage to identify even with radio data, even without millimeter survey. So we will lose information, but and we don't gain much here. So probably 1 mm, if you can do only one wavelength, is probably a better idea. And typically for ALMA, it really doesn't advocate to do 2 mm with ALMA. We have also predicted that there is a bias in temperature. So essentially you have the temperature as a function of redshift of the source. So the gray is a sort of the average in the simulation. The blue is the 1 mm selection, the red is 2 mm. So the red is biased, the blue too, but the red is even worse. So what it shows is, and we know that since ages, millimeter survey are biased toward colder SEDs, but 2 mm make it even worse. So we have two problems. We lose sources at intermediate redshift, and we get a stronger bias. So I would say at this stage, 2 mm is probably, now that we can do two at the same time on very big depth, probably not the best thing to do. So we have now a very new cool survey of large volume, which is very complementary from what ALMA is doing. And if we take all the resolution effects, now we can really see that there is good agreement between the various galaxy evolution model and the circumference. So basically, these start to be better understood. We are almost at the confusion limit in Goose now for a pretty large area, which is really cool. And 2 mm properties of sources are compatible with expectations, so we have nothing weird, but that just say, okay, nothing weird is found at 2 mm, it could have been possible, but now that we know that, I think, I had not a lot of time, but I convinced you that 1 mm survey are probably more efficient to probe the IZ universe, so that's probably where we should push our effort. As Matt was saying, we have to choose now, so the choice should be there. Thank you very much.
Questions?
What are the typical resolution in these images? What is the typical resolution of these data sets?
I'll show it at the beginning. So it's 12 arc second at 1.2 millimeter and 18 arc second at 2 millimeter. So 2 millimeter, it's a big beam. So you really have to understand the effect of confusion. It's not something you can take it lightly. But now we have lots of simulation with clustering and everything to understand it, but it still remains not so easy. The problem is interferometer like ALMA are not so efficient to map a wide area. So until we get maybe a multi-beam array, which will probably take 10 years, it's probably the best solution to make big survey and then pinpoint with an interferometer the beams where we detected something.
So what are the measures you're going to take to take care of the confusion limit in your images? I mean, your images are going to be confusion limited.
No. We approach the confusion limit, but we can't break it. It would require like 2,000, 3,000 hours. So basically we stop here. We won't push more. It's already a huge program. So from the ground on a 30 meter, it will be too hard to reach the confusion. So we approach it, so it's not a problem yet. But still we have to take into account not really the confusion limit in terms of absolute limit to extract sources, but that's the blending between small biases. It's not huge thing, like sources are not fully artificial, but you know you have this 20% average flux boosting which start to appear because of clustering of galaxies that you still need to take into account. But that, now models tend to converge and we have better understanding of physics, so it's something we can correct. After, if you want to enter in percent statistics, it would be a problem, but I think we have so many uncertainty in galaxy physics that it's probably not worth the effort, I would say, at this stage.
Well, I don't think we have much more time for the questions, so maybe if you want the coffee break. So thank you very much. Now we have Stefano Berta from EPM, and he will talk to us about the evolution of dust cosmic density as seen by the universe.
Okay, thanks Mathieu for the nice introduction about N2CLS and everything we can do, except the study of the evolution of the dust cosmic density, which I'm going now to present you. So a little bit of motivation. You've seen this plot already in his talk. The star formation rate density as a function of redshift of star-forming galaxies. Okay, thanks. You see, this is our infrared galaxies. So basically, it's the dusty star-forming rate density. Above redshift 3, 4, you have that this dark red line and shaded area, which still keeps to be quite high, which means that there is still a considerable amount of dust at high redshift. So if you plot the ratio of infrared to total star formation rate density, you see that again above redshift 3, 4, 5, it's still 60 or 70%. Again, a lot of dust is still there. This on the bottom is the spectral energy distribution near, mid, and far infrared of a typical star-forming galaxy, dusty again, reproduced with dust, a combination of these different dust components. So in blue you have PAHs, polycyclic aromatic hydrocarbons, emitting the near mid-infrared. In green, very small grains, dominating between 20, 40 microns more or less. And in red, you have big grains that are dominating the sub-millimeter and far infrared. And the big grains are actually those that make the bulk of the dust mass, okay? Because they are big. So that's why we are now studying the dust evolution, so to say, or the dust content in the millimeter. If you take into account redshift, everything will be shifted there. You've seen this map already. The goods north as observed by NICA 2, and a small comparison to previous surveys in goods north, blank field, so the whole field. We are basically a factor 3, 4 deeper than what has been done before at 1 and 2 millimeter. In this region, we have measured 120 sources at 80% purity, as Mathieu said. And this means down to 2.5 more sigma. But we need to study, to perform a statistical analysis, so we have to cut this number of sources to a significance of 4.2 sigma, which gives us a purity of 95%, so basically helps us to throw away everything that could be spurious, so to say. And we are left with 65 sources. So we heard before 700 sources with Euclid, now we have 65. So the good north, you know, is a very famous field. We have all possible data, from the X-rays all the way to the radio, Chandra, Spitzer, Hubble, JWST now, Herschel, from ground-based, VLA, and all possible optical telescopes. So this is a NICA source observed. This is a 1 millimeter, 1.2 millimeter source, and we need to match this to every other possible kind of data. So this is NICA here on the bottom. Like you have Scuba. This is Herschel. 7100 and no, sorry, this is Spire, so 250, 250, 500. near infrared here, mid infrared with MIPS, and then HST. In this case, it's very fortunate. I mean, the source is one, very well identified in NICA, and is very isolated in all possible bands, so the match is easy, done. Unfortunately, this is not the typical case. The typical case is more like this. You have still one nice source in NICA, maybe also in Herschel, but then when you go to the mid, near, and optical wavelengths, then it's a mess. So to make, I remind you again, the beam here of NICA2, so the PSF, is 11 arc seconds in this band and 18 arc seconds. This means a lot of possibly a lot of galaxies there. So we need to build a multi-wavelength ladder. We need some high resolution, high spatial resolution observations, or as close as possible to NICA, like either millimeter or radio, or maybe some millimeter. And with this, we can pinpoint the position and then find what is the counterpart in all other possible wavelengths. So you see these crosses here. These are radio sources. In this specific case, the radio source is telling us which one of the various of the galaxies that we see in other possible wavelengths we have to pick. This is not, unfortunately, also not always true. Because, for example, in this case, we have many radio galaxies within the main the NICA beam. So then we have applied for our own NOEMA data. So NOEMA is observing also, if you want, at 1 millimeter. And we have a nice, clear pinpoint detection with NOEMA, which is instead this X here. And with the X, we can again find the counterpart. In this case, up to IRAC, this is optically dark, so there are no HST and not even JWST. We have done this for 27 targets. Most of them, only one is not detected by NOEMA. And 5, in fact, are now to be double. So when you have a double, then you will have to do something about Herschel, for example, which has even a bigger beam. And the easiest thing to do is ignore Herschel, because you cannot really, I mean, well, if you have something like this, it's impossible to blend it, okay? So what we have in the end is a nice LCD like this for all of our, at this point, 71, 68 actually sources. 71 in total, because 5 are double, but only 68 have a redshift. So, as you see here. This is our redshift distribution, which is cut, but anyway extends up to redshift 7. And with these nice LCDs, you can do everything you want. So we are fitting them in all possible ways, with modified black bodies, with Drainelli models, which is only far infrared to millimeter, and then with UV to radio models, which are MAGFIS, SIGAL, or this LCD. These are some examples. The 3 boxes on the left are the same source, okay? So a modified black body, Drainelli, MAGFIS, and SIGAL, they all give very nice fits, and in the end you will see the result on the dust mass. And on the right you have a case that needed an AGN torus to explain the excess here in the mid-infrared. You could not explain it with only stars and dust. So the end result is a dust mass, what are we interested in, and we can compare the dust mass obtained with all of these methods, each method against each other, and within each one has their own limitations. So, but within all these limitations, we can say that basically, if you just, for example, check the last column with SIGAL and against all the others, if you are a fan of SIGAL, they are more or less. They all give consistent results in terms of the dust mass. Other parameters are much more difficult to constrain than this. With the dust mass, I will skip 1,000 steps, and we derive the dust mass function. Okay. So on the left, you have our own determination, which are the red dots, compared to the literature. So we split it in 3 redshift bins. We have, remember, only 65 sources, so we do what we can. Here you see only those bins for which the complete mass completeness is above 50%, and that have at least 2 sources. Okay, well, the error bar is only a Poisson error in this case, so the number of sources is significant in all these. There are basically only two main works that pushed to high redshift so far before us. One is Pozzi 2020, who basically stopped at redshift 2.5, and Traina 2024 arrived to more or less redshift 6. Again, we are consistent with the literature, and on what you see on the right instead is a Schechter description of the mass function obtained using the STY method. So this is not a fit to the red point, okay? The STY is basically a statistical method that takes into account the contribution of each single galaxy given their mass and the uncertainty on their mass to the mass function. So in this way, we can take into account the uncertainty on the mass of each galaxy without having to deal with error propagations, which would be very, very difficult to deal with this in this case. So combining this, our result, or Schechter, to the literature, we see basically an evolution of the dust mass of the galaxies from redshift 1 more or less to 3. So strong evolution of mass up to redshift 3, and later instead from 2.5 to 7, a strong evolution of the density of these galaxies. You integrate the Schechter, yeah, and we derive the rho, so basically the dust mass cosmic density. We see this sudden drop above, let's say, beyond this node. This is in the look-back time scale, okay? So it's a bit different from what you're used to see. It's not completely wrong. It's just different way to scale it. Okay. Oh, it died. No. Okay. Sudden drop, and compared to the literature, already you see here at high redshift where we are sampling the rho, there is a large scatter. So if you go to lower redshift, the scatter is also becoming even more dramatic. The problem here is that there is manifold. So the first thing that is very, very important to do when you do this kind of comparison is rescale everything to the same assumptions on dust properties. And the first parameter that one encounters when doing all this work is this dust absorption coefficient, kappa nu. Each work is having their own preferences, so you have to rescale everything to this, both during the dust mass function comparisons and also now in the rho. And this is not done very often, frankly. But still, even this is already rescaled, and you see the scatter is terrible because probably there are also other assumptions that are different. The method, the models that one is using, and so on. This is a comparison to evolutionary models. There are semi-analytical models here. There are chemical evolution models. And again, I mean, except for a couple of models that are completely off, and it's easy to rule them out, here they all predict everything and also the opposite of everything, except for the sudden drop at high redshift. We all agree on that. But for example, at lower redshift, some are more flat, some other increasing, predict an increase from low redshift to cosmic noon, let's say. Some others are the opposite. And to really figure it out, in my opinion, we need like a big blank field, deep, so to be able to minimize the error bars, but also to have an estimate over the whole redshift range, or as wide as possible, using the same assumptions, self-consistent. Or if you want, you can reduce and redo the whole analysis on all other samples, but probably it's a bit difficult. So take-home messages. We have, with the good north blank field, 71 sources. 68 have a robust redshift and very nice SED. Different methods agree in the dust mass estimate within their limitations. The mass function is extended to redshift 7. We see mass evolution up to redshift 3 and up to redshift 3 and density evolution up above redshift more or less 2. Consequently, there is a steep decrease of the rho. at very high redshift and a mild decrease from cosmic noon to now. There is a wide scatter, so this is calling for more self-consistency on the method and the assumptions, and so big field probably and deep. And it's very, very important to always take into account to rescale everything to the same assumptions, if comparing to the literature. I leave you with some publicity for the N2CLS publications. So, well, I'm not going to comment on this, but if you want to take notes, this is what you're going to see very soon on the SOPH.
Thank you very much. Questions? Yes.
Yeah, thanks for the very nice talk. Just a quick question. I was wondering whether you try to, given that you have a large field of view, maybe you can have the position of sources from other catalogs, whether you actually try to stack to see if you would get more detections.
No, we haven't done the stacking. So but I know someone alive in the back who did it on the ALMA collection, a cube. Basically selecting in the near infrared to then derive the dust mass evolution of stellar mass selective galaxies, but we have not done it here specifically.
Any other questions? I have one actually, because you said you tried several different methods and you showed the concept of this. So what would be your favorite method, or the one that you would recommend to the community to use?
So, okay, we can do this. But it depends a bit what data you have. For example, if you have only this kind of SED, so let's say far infrared, a millimeter, which is pretty common, unless you have a famous field with all possible follow-ups, or it's very difficult to have an SED like this. Then here, if you have some mid-infrared, I will go for Drainelli, because Drainelli needs the mid-infrared to constrain the warm dust. Otherwise, I mean, you are somehow limited to modify that body. And then someone will tell you, you need to use optically thick or optically thin. There is, I don't know if she's here, probably she's coming tomorrow. It's been demonstrated that, unless you have really high quality data, you cannot go for the optically thin. I mean, you will have too big uncertainties. If you have a nice SED like this, all these codes give you the same result, basically. So, I mean, if you are in the French community, you want to use Seagal. If you are in the other French community, you want to use McFish. If you are in the UK community, you want to use something, AGN filter. I mean, it doesn't matter.
Thank you very much.
Okay, so we start the new session. So the first speaker is Roland Bacon, who is going to tell us about the Wide Field Spectroscopic Telescope.
Okay, thank you. So good afternoon. So I'm just going to do full screen. Okay. Okay, so I'm going to present the Wide Field Spectroscopic Telescope. A long-term project, and I'm happy to see a lot of young people because it's for them, clearly, not for us. That we are currently under the concept study, and that we plan to propose as ESO as the next big project after the ELT. Okay. Why now? It looks like it's far away, but you see this project in the ELT took 30 years to be there. So we have to think a bit in advance, and I think it's the right time to channel new ideas and try to be prepared to what maybe may become a very important facility for the European community. So, okay. So I'm speaking on behalf of a very large consortium of European institutes and a few universities in Australia that is starting to to think about what could be this next big project. We have also, in addition to this big consortia, a very large science team, which is open. So if you are not yet there, please feel free to engage yourself. And so it's currently 500 members. And then to start with us to think about what sort of science we would like to do with such a facility. So in France, there is currently in the consortium itself 5 institutes. So it's led by CRAL. We have IP2I and Saclay and LAM and Lagrange currently. So this project is in a way the answer to one of the ground-based priorities, there are 2, of the astronaut European roadmap, which has been delivered recently. It's also clearly in other roadmaps like the US Decadal Review, Canadian, Australian, and many others. And the reason is that it is the facility that we need to follow up, also to go with the current large project that we are doing, such as using Euclid, LSST, and many others. So we know how spectroscopic surveys have been so important for our field, because they provide very homogeneous sample of spectroscopic data, which can provide physical information, kinematics, very precise redshift, and many others that you cannot get from broadband imaging. Okay. We know extremely well what has been the results of the SDSS, which was at the time a relatively small telescope, but which was seen as a facility, and that has really get a lot of science results, and still getting. EFU or EFS spectroscopic survey are more recent, but they have already shown that they can provide very interesting results on nearby galaxies, such as Sauron, Calipha, Monga, and others. And recently with MUSE, it can address also the distant universe, high redshift. Okay. So these are completely different approach by scale, by field, by the way they operate. But in a way, they are very complementary. And WST is really the idea to join these 2 approaches by building a spectroscopic facility of a 10-meter class telescope that will have a very advanced MOS, much higher multiplex than we currently have, and a giant panoramic EFS, both working in synergy. So the top-level requirement we have set for that is first the telescope aperture. So we came up with a 12-meter size telescopes. So currently it will be an aperture factor 2 bigger than the VLT, but with a very large field of view. And you can see that the field of view is 3 square degree. And with a spectral range covering the optical and the near-infrared. It's a facility, means that you don't build the telescope and then you add instruments. You start to think of building everything together with the money you can get. And this will have 2 instruments, only 2, but 2 very innovative instruments. The first is a MOS, a multi-object spectrograph with 2 modes. The one has a low resolution mode with a multiplex of 20,000, say a factor 10 larger than we currently are doing with existing MOS, medium spectral resolution, and which operate in the visible, simultaneous access to all the wavelengths in the visible. The infrared is seen in a later stage for technical, cost, and feasibility reasons. I can come back to that if you have a question. The second mode is a high resolution mode, mostly for galactic studies, but probably could have some interest in extragalactic as well. So lower multiplex, but very high spectral resolution, 40,000, with such a big aperture. And also will not cover, of course, the full wavelength range, but 3 to 4 regions to be defined in these wavelengths. The second instrument is a monolithic intergraphy spectrograph with a huge field of view of 9 square arc-minutes and a spectral resolution of 3,500, and which cover also the optical domain in one go. So it's more or less muse plus blue muse multiplied by 9. It has also the opportunity to do a mosaic, and I will come back to that again. And then there is two top-level requirements in terms of operation, which are extremely important. The first is that we want the MOS and the FS to operate at the same time. And you will see how this can lead to new science if we can do that. And then, because we foresee that this is a field that will become so important, target of opportunity which shall be implemented at the telescope and at the fiber level. Just the field to show you a comparison. So you show the field of the MOS here on the top, and to be compared with the field of the VLT here, and the field of the ELT. So we show how big it is, and this is why we don't go to much larger aperture, because it's difficult to manage very big field and very big aperture. And in the center, at the same time that you are doing the MOS, you have a field that you send to the EFS, and you can have a 3x3 arc-minute EFS compared to MUSE. You see how bigger it is. And the idea is that while you do multiple observations, which are usually needed for MOS because of the clustering of sources, you can do a mosaic of a much larger field of view at the same time, or doing very deep on one smaller field of view. So in terms of comparison, this will be a really unique facility. So if you compare the multiplex and the telescope aperture, you can see that WST stands out of all the existing facility, and there are only some plan one which can be compared with MSC, but with smaller field of view. So this is proportional to the étendue, which is roughly proportional to the speed you can do a survey. And which makes it completely unique is at the same time you have that, you have the WST EFS, with a field of view which is completely unique, and having both. I just want to mention that here you see that there is the ELT business, and in that field, the ELT will not be competitive, because they have, by construction, a small field of view and a small étendue. So they will do very different things, of course, but in terms of getting access to a very wide, big sample of spectroscopic data, only WST can do it. And this is, of course, the same for the EFS. So, the current design is a telescope, compact Cassegrain configuration with an F1 primary. So it's based on 78 ELT segments. So we are planning to use exactly the same ELT segments, of course. We don't want to reinvent the wheel here. It will be, ESO has invested a lot of money into the ELT, and we are going to reduce that. So the large 2-degree field of view is sent to a field corrector, which also acts as an atmospheric dispersion compensator. And the F3 beam is then focused to the positioner. The fibers are connected to the triple arm spectrograph and the high resolution spectrograph, and there is a pickup mirror in the field center which sends the light through the coup de focus, which see an optical derotator, and then go to what we call an EFS station that you can see here, which is 144 spectrograph. And you can see why you need to design a facility. The volume used by the instrument are almost as big as the telescope one. Okay, so the potential site will be done in parallel for a number of obvious reasons. It's a very good site. It's also much more sustainable to build rather here than deriving a new site. And we can use the existing parallel solar plant to benefit from good energy and save a carbon impact. So the science case is wide. I have not much time to develop it in detail, but I will discuss a few cases in the extragalactic case, which is the topic of today. And I just want also to show that there is a very strong synergy with existing facilities. I say LSST, Euclid, SKAO, the Einstein telescope, the LT, and Gaia. So one example, just one example, will be to reconstruct the dark matter distribution with extremely high fidelity up to a redshift of 1.6. And for that, you can complete that with a survey of a 50 square degree complete survey with a few million galaxies. And from that, you can study the distribution of dark matter. So this is a model of dark matter, and you can see it with the light cone and one example at a redshift of 0.6. And from that, you can see what will be delivered by Foremost or DAISY, the formator. And you can see it can recover, of course, significant part, but it's really limited by the depth of what this facility can do on the formator class. LSST, of course, will do much better in terms of depth, but then the precision of the photometric redshift is the limitation. And you can see that you cannot recover very well the distribution of dark matter. This is what the WST will do. And from that, we can identify all cluster structure down to the Milky Way halo at the intermediate redshift. This will yield a direct map distribution of the evolution of dark matter of the past 8 billion years. And so I think it's a very important topic. So in addition to that, the FS can probe, for example, here, the cosmic web by studying directly the emission of the filament of the gaseous emission of the gamma. We can do tomography. It seems that I'm short in time, so I skip the cosmology part. And just one last example, it's the EFS-driven survey of massive galaxy cluster. So you can study in the center the strong lengthening region with the FS, which is a good size, and the external part, you can have access to the weak lensing, and then you can connect the distribution of the filament with the cluster itself, and you can do that with a number of elements. So the number of sources that is expected for such a survey is huge. It's huge. Doing the same with MUSE will need 40 years of MUSE, or 400 years with Foremost. So it really can address a completely different perspective. This is the timeline of the study, and just want to mention in yellow, this is ESO has decided to launch the process to decide for the next facility. And the decision timeline is really compatible with what we are doing. So even if you see that, well, it's such a long-term project, the decision to go that direction will be taken in the coming years. So it's critical time for such a project. So what role can do the French community on such a big project? I think we can pretend to play an important role, maybe leading, who knows. At the end, we'll be led by ESO, but we can pretend to have it. First, we are leading the concept study, but more importantly, we have a very important expertise in MOS, in FS instruments. There will be challenge. It's clear that today, the way we are doing the LT instruments, cannot be expanded to bigger. It's already, so we have to change the way we operate, so some different way to operate it with ISO. This is to be defined. And data handling will be key. Of course, you can remember that the SDSS effort in terms of cost and FTE was probably more than half went to the data reduction and data handling. And so there will similar effort will need to be there. This is something that ISO is not going to do, and this is ISO something that the committee can do and will have to be done. And this is something where we have to be prepared, because it's a fantastic endeavor. So I end up here with a summary you can read, and I take any question you have.
Thank you, Roland. We have time for maybe a quick question while the next speaker is getting started.
Just have a quick question. So, what are the challenges that one would face with the WST data? Because we are going to expect so many detections of sources. So, in terms of source detection and classification, what are the challenges we are going to expect from the WST? Or are we experienced enough with news and we don't have any challenge?
I think, yeah, there are many challenges. I think the challenge the number of objects, but number of objects in a way for LSST will be much larger, but it's the complexity. I think it's different to do photometry and to deal with data cube or spectroscopy. And of course, we have to define all the process that go to get automatic redshift, automatic measurement in a way this is homogeneous and so on. So this is clearly a challenge that we have to face. We are parts both in Muse, for example, and Blue Muse later on, but we are also part on Formos and other instruments. So we have the tool maybe to develop that to the next scale. But it will have to be developed to the next scale if we want to meet this challenge. I think this is mine.
Okay, the next speaker is Louis Quillet, who is going to tell us about galaxy morphology and photometry with Euclid.
Hello everyone, my name is Louis Quillet. I'm a postdoc here at CRAL, and I'm going to present you a study made on the early release observation of Euclid, which is the first morphological description of galaxies as observed by this new space telescope. So first I'll start with a bit of context on galaxy morphology. So galaxy morphology is a topic as old as galaxy science, as it started with the early work of Edwin Hubble, which classified galaxies according to the shapes and features that he observed, leading to the establishment of the well-known Hubble sequence that you can see here on top of the image. The galaxy morphology has then been used in many landmark developments of galaxy evolution. It was, for instance, linked to the color bimodality of galaxy population, which you can directly see from these images with the spiral types and irregulars that are really blue compared to the redder ellipticals and lenticulars. It's also connected to the environment via the famous morphology density relation. During my PhD, I focused a lot on studying the Hubble sequence in the local universe, and what I show mainly is that the Hubble sequence can be seen as an evolutive sequence, which I sum up here with one diagram, which is a polar magnitude diagram with UV to optical colors. And what you can see is that if you look at specific Hubble types, you have the irregulars at the faint end, and then you have all the types of spirals that go through the blue cloud, or the main sequence of star-forming galaxies, the same blue star-forming galaxy. Then you have the estate type in the green valley, and then the red sequence of passive galaxies formed by ellipticals and lenticulars. And it's also valid for other relations, such as the size luminosity or the Cormendy relation, where you see that the Hubble sequence spans this diagram, and therefore morphology is a key component in galaxy evolution. So to further investigate this issue, I have started using Euclid data with Hero Perseus images that Jean-Charles mentioned earlier. So we have images in the 4 Euclid bands, plus complementary survey from Megacam. These are a bit deeper, these images are a bit deeper than the wide survey, and you have an area of roughly half a square degree which corresponds to a few thousand galaxies at the magnitude that we will be interested in. So here on the left, you can see an image that you surely have seen a lot these previous months, which is the full Perseus cluster images. But what's so interesting about this image is that wherever you zoom, you can find a lot of few thousand galaxies, and I really recommend you to do that, to download the image. So here on the left, you can see an image basically all the part of the galaxy within this inner ring, which is model, which lead to this bad residual image. So you can see the power of Gaussian disk decomposition, which is much more interesting than a single thoracic fits, and also the biases that it will lead to. And this is the topic of this analysis, is to compare the two methods and to see the consistency and biases in the morphological description and what we can learn from them. So the idea is to compare the parameters and try to see how they relate to each other. So we'll start by doing this with the galaxy sizes. So we get from the modeling an effective radius, so it's an half-life radius. So since it's an half-life radius, it should follow this relation, where the effective radius of the bulge is lower than the one of the galaxy. So the 1p is for single profile, so it's galaxy modeled as one profile only compared to Gaussian disk. So which itself should be lower than the disk. And if you look at the images that we obtained for the Euro Perseus images on the top left, what you can see is that you have along the diagonal line, which is the line for which the bulge and the single profile gives you identical results. You only have red points, which corresponds to galaxies that are pure bulge, B over T close to 1, which is consistent. You have the same consistency with the vertical trend of galaxies, which are pure disk, where the disk and single profile leads to similar results. And then within this upper right triangle, you have a gradient of color. And basically, how intermediate the effective radius of the single profile is compared to the bulge and disk depends on the B over T. So you can see that the position of this radius on the segment defined by these two extremities is a linear function of B over T, which is shown here on this plot. This is important because it can help producing better mock catalogs, having this kind of relation between all these radius, but it also raises a warning of how we interpret this kind of measurement, because half-life radius is a measure of the extent of a source, but also of its concentration, as we can see here. So if you try to infer things from the evolution of RE as a function of redshift, you should be aware that you're mixing these two components when you only have the single thoracic value. And so for spirals and lenticular galaxy, it's really important to decompose your galaxy to obtain physically meaningful interpretation and not mix difference in concentration and extent of your galaxies. Another interesting correlation that we can see in the top left plot is the correlation between the single profile thoracic index and the bulge to total light ratio. It doesn't seem very clear here because there's still a lot of outliers, but you have this diagonal sequence which corresponds to the good fit, while the other one were inspected and actually are more spurious fits or problems with contaminations and so on. But what this rough correlation tells us is that both of these quantities are actually proxies of the morphological type of a galaxy, because thoracic index indicates steeper profiles, so more concentrated objects, and B over T also indicates a more concentrated object. You can also analyze trends with the thoracic index of the bulge itself, which leads to show that there are continuous transition from small pseudo bulges to more to bigger classical bulges. Another biases that is really important that we highlight in this study relates to the inclination of galaxy. Galaxy inclination are really important when you want to look at the alignments of galaxy. We know that these are not random. The galaxy spins tend to align with the cosmic structure, so a lot of studies of intrinsic alignment of galaxy or for cosmic shear studies rely on a precise measure of the elongation and position angles of galaxy. And what you can see here in the right example for this very edge-on disk with the bulge is that the single thoracic profile doesn't do a great job at the modeling because it cannot fit both the disk and the bulge. So it does some kind of middle ground, which is the inner disk and the bulge, while the bulge and disk decomposition does a great job at modeling both structures. And this has a large impact on the measurement of the elongation, because the elongation of the single SOSIC is 0.27, while the one of the disk component is 0.13. And more globally, what we can see is that as long as you have a very small bulge, you have no bias between the elongation of the single profile and of the disk. But as soon as the bulge becomes prominent enough, you have a discrepancy between these two values, with elongation in single profiles that underestimate the actual elongation of the disk. And this effect gets worse for disks that are more inclined. So if you want to properly measure the disk elongation to look at the spins of spiral galaxy in relation to each other or to the cosmic structure, it's well recommended to use bulge and disk decomposition, otherwise single SOSIC profile measures are going to be biased by the bulge. The last bias that I will talk about relates to the photometry, because so far I've been describing the structural parameters that explain the morphology, but this has also consequences in the photometry that you measure from them. So there will be differences between aperture photometry and model photometry, but also between the different modeling choices, so the different model photometry that you can obtain. On the left plot, I show the adaptative aperture photometry in comparison to the single SOSIC profile photometry. So these two are defined differently because one of them is integrated to infinity while the other is an aperture one. So, but this can be computed, I mean, this just difference can be computed, and it's a black line that you can see here, while the blue point are the actual differences. And you see that for low value of the SOSIC index, you live above the curve, which can be interpreted by the fact that in this later type of morphology, so spiral galaxy, you have a lot of flocculence and clumps that won't be modeled, but are seen in the aperture photometry, which leads to a brighter aperture photometry than the model. While for later, larger SOSIC index, you have an issue of like overfitting at the center and overestimating the model. On the right side, you have the difference between the bulge and disk decomposition and the single profile. And the one thing to get from this plot is that since we have a rough correlation between bulge to total and n, as long as these two components sort of agree between each other, you have no offset. But if you go to higher value of the SOSIC index for a given B over T ratio, you end up with more fluxes in your single SOSIC profile, while if you go to lower SOSIC index for a given B over T, you end up with less flux in that profile. From this photometry, we can compute colors. From the photometry of the bulge and disk composition, we can also obtain photometry separately for the bulge and the disk, which is very valuable. So here I show you the colors for the bulges and disk in the European images, and we retrieve the known results that bulges are on average redder than the disk, in agreement with a lot of studies. And we also have a morphological effect, which is the fact that for small BT galaxies, for like spirals, there's big differences between the colors and the bulge and the disk compared to larger, so like lenticulars and ellipticals, for which the bulge and disk have the same colors. And finally, we highlight in this study color gradients. So when we compare the structural parameters in between bands, you probe different stellar population. So by looking at how they vary between the different bands that you've used, because you've done multi-band fitting, you can infer things about how the stellar population are located within your galaxy. And we highlight both single SOSIC profile, but also separate disk color gradients. So which means that you have more star formation at the outskirts of your disk than in the center. And I will let you here with my conclusions.
Any questions for me?
Just on the slide before, you showed you mentioned gradients. It was a bit quick. So And this line about age versus metallicity gradient versus dust, can you comment a little bit on that?
So yes, what we measure is, so we look at the differences in the effective radius or in the stochastic index between, so for the same modeling method, but between the different Euclid bands. So the thing is, if you have different stellar population, they will have different colors. But if you have different dust distribution within your galaxy, it will also impact. And if you have different, the color of the stellar population is both age and metallicity gradients. So all of this is mixed up. So that's why I cite this paper from Bias that's trying to do some modeling to give an estimation of how much these effects were important.
Distinguish? Yeah,
to disentangle the two. I mean, you cannot really disentangle age and metallicity, but you can disentangle dust from age and metallicity if you probe the right bands that we do not have here in this study.
Okay, for the sake of time, I think we need to go ahead. So thank you, Louis, again. Next speaker. Hello, as you want. Okay. Okay, the next speaker is Héloïse Bernot, who is going to tell us about extended UV galaxies with deep optical photometry.
Thank you. Hello everyone, I'm Héloïse Bernot, I'm a second year PhD student, and I'm going to present you my work on the characterization and the properties of nearby extended UV galaxies with deep optical photometry, and more about the relationship between giant and low surface brightness galaxies and XUV. No? Okay. My work is in the context of the low surface brightness galaxies, and if we look back to the 70s, we didn't know that these kind of galaxies exist. And Freeman studied the sample of galaxies and found that the central surface brightness of galaxies follows a Gaussian distribution with a peak at 21.65 magnitude per second square. And in the next few years, we found low surface brightness galaxies as Lyon 1, that is the most giant LSB known. And we can see there is a faint and large disk. And more generally, Mago found that with a sample of nearby galaxies, there is a lot galaxies like Malin 1 and with fainter central surface brightness than 21.65 magnitude per second square, and they don't follow the Freeman law. In 2003, there is the UV NASA mission Galaxy, and with this mission, Gilles Depasse discovered the first extended UV galaxy. So, what is an XUV galaxy? It's a galaxy with UV emission beyond what we call the R25, and Tilker defined properly these galaxies in two types. So the first type, it's UV emission, so beyond the R25, and structures emission like arms, like we can see in this image, while in the optical we don't see anything. And for the second type, we saw partial emission beyond the R25, and in the optical we can see a large blue LSB area. And the field expanded with the discovery of a large amount of galaxies, of a large amount of ultra-diffuse galaxies by Van de Koom, and we hope more studies and more discovery in the next few years with LSST, Castle, and Euclid. So, to remind what is the difference between a low surface brightness and giant low surface brightness, we have to come back to Freeman. And Freeman separates the profile of surface brightness of galaxies in two components. So the first is the spheroidal component, and the second one is the exponential component. And by fitting the exponential component, we can have the central surface brightness of galaxies. And with that, it's probably proposed to take the central surface brightness of galaxies with the scale length of this component of galaxies and put this data on this diagram. And we can see the Freeman value that separates the normal surface brightness galaxies from the low surface brightness galaxies. And the, thank you.
Take it away. Yeah.
Yeah, thank you. The green line here separates the giant low surface brightness galaxies, and we can see Malin 1 here, from the low surface brightness here. And the giant low surface brightness that I just showed you, some people found that some of them are both XUV galaxies and giant LSB. So the questions that we can ask are giant galaxies, giant low surface brightness galaxies and XUV are the same family, are distinct families or galaxies, and have they common properties? So, to answer to this question, the sample of my study is 9 galaxies from the paper of Tilker and that are available in the DES data. And the first example that I took is NGC 1042 because it has already been studied in many papers with many data like Dragonfly and LBT. And the method that I use is similar to the paper of Merit 2016. So I binned my images, I masked the galaxies surrounding and the stars, and I fit ellipses to have the central surface, to have the surface brightness profiles. And so this is the profile that I have for NGC 1042 in the GBAN. So in the first panel, I compare the red line, it's the profile of Trujillo in his paper in 2021 with LBT data, and I reproduce the method that I use with also the LBT data to compare if the method that I use is following also if it's consistent, and we can see that the green line, so my method, is following the red line. So the method is good. And the second panel, it's in red, the same profile with LBT data of Trujillo, and in blue, it's the method I use with DES data. So we can see that DES data allow us to study the extended UV galaxies. And with that, I apply the method in all the bands of DES, so G, R, Y, Z, and Y, and also with the 2 bands of galaxies, so far UV and near UV. And to study the extended disk of these XUV galaxies, I need to find for all my sample what we call UV radius. So for that, I calculate the star formation rate surface density of my sample, and for the same value, I took the radius corresponding. So the value that I chose is 10 to the minus 2 solar masses per year per parsec, and this value has been chosen in comparison with the paper of BGL that is studied a sample of nearby galaxies, and this value corresponds to the extended disk, extended part of the galaxies, and with the paper of Journées that he reproduced the same with Malin 1. And with all of this, I can now studied the XUV disk of the sample. So for that, I just apply an exponential fit on the center part of the galaxy and another fit in the XUV part of the galaxy. So from R25 to RUV. And for each galaxy, I have 2 scale lengths and 2 central surface brightness, as you can see here. So I reproduce the same with already existing profile for Malin 1. And with my sample, I found that there is 3 different families. So the first one is these 3 that are Malin 1-like. So the cross symbol is the fit for the XUV disk, and the square symbol is for the center disk. So we can see that the XUV disk is close to the separation with the giant LSB, and for the center it's more. This looks like HSB. For the second family, it's 3 galaxies that are completely LSB. So the center and the XUV part are LSB. And the last family is the Malin 1 opposite. So the XUV disk looks like HSB, and the profiles are truncated. So that can explain. We can explain that. So in conclusion, we can use the test data to characterize the optical properties of the extended UV galaxies in the region between R25 and RUV. And we found different behaviors and 3 different families for this XUV. So the Malin 1 opposite, the Malin 1-like, and the galaxies that are completely low surface brightness. And the next step is to find another way to characterize and diagnostic these XUV galaxies, and also analyze the stellar population with the color profile and the sensitivity. And we hope to apply this study also on the CASTLE data. So CASTLE is the telescope in construction at LAM, and the main science case for this telescope is to study the low surface brightness. So we hope better images with less noise. Thank you.
Do we have questions? Maybe I have one. So you talk about the CASTLE telescope, right?
Yes.
By how many galaxies do you plan to observe and to study? Like 10, 100, maybe more.
I don't know really, because it's ongoing and it's not ready yet, and we have to discuss more.
But it's going to be it's a relatively small demonstrator, and so we need to spend a lot of time on each galaxy. So it will not be huge samples for sure, but it's a very big field, so we can do the big ones.
Very nice. Thank you very much.
Thank you.
Okay, the next speaker is Quentin Baston, who is going to tell us about exotic strong lensing.
Thank you. So, hello everybody. So I'm Quentin Baston. I'm a PhD student at CRAL, so here in Lyon. And I'm working on massive galaxy clusters and strong lensing. And today I'd like to present my work on what is called exotic strong lensing. So why is strong lensing important in our field? Because, as you may know, those are powerful natural telescopes to probe the very distant universe and some regions that could not be observed without those objects, even with our instruments. The observations can help us to address some cosmological challenges, for example, to trace dark matter and its distribution in those clusters. And finally, thanks to the distortions, the multiple images that are available with strong lensing, we can have numerous observational constraints for improve our clusters models, and this provides us unique structural characteristics for clusters. So now, what are exotic lenses? What do we know about them? So those are very specific case of strong lenses because they give rise to high magnification factors, very high, so that could be above 100 at the inner core of the cluster. They also give rise to a larger number of multiple images in comparison with classical strong lenses observations. So we have usually 4 multiple images plus 1 counter image. And what is very useful is the fact that those images are not centered at the same location as the mass barycenter of the cluster, so that it's very easy to look at those images because it's not very polluted by the BCG, basically. On top of that, those exotic lenses are characterized by image distortions which are mostly isotropic, so this is very useful if we want to understand how are structured the sources. And the only problem is that their observations are very rare. For the moment in the literature we have less than 10 exotic lenses which are known. So this is one of the questions. Why can't we observe more of them? So I will explain that it is mainly because those lenses require very precise geometrical conditions to appear, and the goal is to detect them. So why are those lenses interesting for us? Because of the high magnification factors, we can have enhanced observations of very faint and very, very distant sources, so to probe the very, very distant universe, more than with classical strong lenses. The larger number of multiple images is also useful to have strong observational constraints for improving the models of clusters and to have access to many details of the structures of the sources. And the fact that the distortions are mostly isotropic is also helpful when we want to have source reconstruction. So this is a way to guide the reconstruction more easily in comparison with classical giant arcs reconstruction. And finally, today we have a need to find a method and a formal definition of what is an exotic lens when we try to identify them easily in big surveys of clusters. And one of the big challenges today regarding those exotic lenses is that we will have access to forthcoming big surveys, very rich, thanks to Euclid, GWST, and so we need today to have very powerful, efficient, automatic methods to find those exotic lenses if we can find them. So how can we formally detect those exotic lenses? So basically what you need at the beginning and as an input, you need a model of a cluster to have access to make it short, to have access to the caustic lines of related to the cluster. So the caustic lines basically are just the points which are theoretically infinitely amplified by the lens. So when you look at the source plane, and for example, here you have a schematic view of what is happening when you have an exotic lens. So when you try to vary the redshift of the source, those caustic lines will spatially evolve in the source plane. For example, you have one green line here and one caustic red line here with a cuspy point right here. And when you change the redshift of the source, those lines will evolve spatially, and at some point you can observe an exchange of this cuspy point between the two lines. And this is at this specific source redshift and at this exact location that you can expect to observe those exotic images. So many images off-centered from the BCG with very high magnification factors, etc., etc. So what we have to understand here, and it is very important, is that you can observe an exotic configuration only if a source is located right here at this exact redshift. So this is, you can understand why it is very rare, it's a very rare event. So now just for you to understand maybe clearer what I'm saying, here is an animation. So what you can see here is the source plane, and here the image plane for this cluster, MAX 1206. And what you can see here are those caustic lines in green and red. This red circle corresponds to this exotic point in which we expect to have the source to produce exotic images. So for the moment, what you can see here is that my white source is not exactly at this location. But what you have here, the corresponding image, is basically what we expect as an exotic configuration. We have 4 images plus 1 counter image. So even if we are not exactly at this location, we have an exotic configuration. And now, just for you to know, when we move this source and make it closer to the predicted point, we have something that looks like a merger of those 4 exotic images, and at the end you have just a big zoom image of the source. So this is the ideal case of an exotic lens, when you have those 4 images just merging as one big image of the first of the source. So a question that I want to address in my project is, how can we define this region in the source plane to be sure that we can observe something exotic in the image plane? Because we don't have an answer for the moment at this question. So what I've done is to look at the source plane and looking at a region where we are sure to produce 5 images. So 4 multiple images corresponding to the exotic plus 1 counter image. On top of that, as I said before, we expect to have isotropic distortion, and we also expect to have homogeneous values for the amplification between the multiple images. So I defined this ratio. So this is the maximum amplification regarding one image, and here you have the minimum of the amplification. And you want this ratio to be equal to 1, just to be sure that the amplification is homogeneous between all the images. And then when I've done this for one specific source redshift, I did the same process, but for a wider range of source redshift, just because we can maybe expect to have exotic images which are produced even if we are not exactly at the predicted source redshift. So I wanted to explore in several dimensions this problem. For example, you have here one result obtained for MAX 1206. So we are, for this image, at the redshift for which we expect to have the perfect exotic image. So here, just for you to understand, you have here a plot corresponding to the source plane. And the color bar corresponds to this amplification ratio. So the closer we are to 1, the more we expect to have exotic images. And here, the purple cross corresponds to the exact location predicted by my numerical method. And what you can see here is that we have 3 sub-regions that can be identified. So the first one is this one, next to the exotic point in the source plane, for which we have homogeneous amplification values near this exotic point. Then, when you are a bit further, you can see that amplification values of the produced images are more dispersed. So why do we have that? And finally, we go back to more homogeneous amplification values, but this time, when you look at the values of the amplifications, those are lower. So this is less interesting because we want to have a very high magnification and amplification factors. So I decided to put, in this example, to put a simulated source in those three regions. And here you can see the three images produced and predicted. Oops. So when you are almost exactly at the location predicted for the exotic source point, you have the ideal case of the merger of the four multiple images. When you are in the second region, you have a more classical exotic configuration with the four images right here and the counter image. But when you are too far from the point right here, you have something that looks like, you cannot see the last image, but there is one image right here, and you have the three here. And this corresponds to what is called the Einstein cross, so we are now not in an exotic region. So finally, I wanted to run all these production of amplification ratio maps for different clusters at different redshifts. And what I wanted to do is to measure the size of the first region that I showed you before. So if I go back right here, I wanted to measure the size of this region that I consider to be my exotic region, in which if I put my source inside, I will have something exotic at the end. So I am able to measure, to take this region, to measure its size, and I've done this for different redshift values. So just by changing the redshift of my source, and I could obtain something like that. And what you can see is that my region is has a size maximum when we are at the exact redshift predicted by my method. And what you can do is also to compute what I call the exotic comobile volume regarding the redshift. And this is a way to quantify the exoticness of my cluster, because the bigger this integrated volume is, the higher the chance of having a source inside this volume is. So we want this volume to be as big as possible to have an exotic configuration. And just to finish this presentation, I want to give you some applications and concrete uses of those exotic lenses. So here you can see a plot taken from a paper of David Lagatuta, for which we have worked on the cluster RxJ. And what we wanted to do is to plot the radially average surface mass density profile of the cluster. So here you have the radius and here the surface mass density. And what you can see here in red is the constraint that we could obtain using only those four multiple exotic images. So we have much powerful constraints using exotic images in comparison with other classical ones. Here what you can see is the image plane of two systems, here on the left, and their source reconstructions. And what you can see here is the fact that we, thanks to the very high magnification factors and the many constraints that we have, we are able to reconstruct very tiny sources. Here it's at redshift 6, if I remember. And those sources can be nearly observed directly by eye when we look at the images directly, because of the isotropic distortion. And one last slide, what you can see here is a focus on one system. So we are looking at the same cluster as before. And those four systems are exactly the same. We are observing the same system. And you can see the substructures of the sources, even if we are just looking at the lens. So the spatial properties of exotic lenses, so isotropic deformation, compact system images, make all of this possible, especially the detection of small-scale substructures. Thank you for.
So did you test your tool on all the clusters, lensing clusters, or a couple of them, or just on one?
This method, I applied this on for the moment on 120 cluster.
So do
Yeah.
you know if these are all merging or group clusters? Have you tried to classify them based on?
Yeah, so I'm currently doing this now. I'm trying to find which parameters of each clusters are giving exotic regions or not. Basically, the first thing that we can tell for the moment is the fact that we want to have a cluster that is very elliptical. If you don't have an elliptical cluster, your caustic lines and the critical lines will be too isolated. Basically, what I told at the beginning is that we want to have an exchange of cust. So we want the caustic lines to meet at some point. And this is only possible when you have an elliptical cluster. So this is one basic affirmation that we can tell, but we are trying to understand if the mass profile of the cluster can have an influence on those exotic regions, and I will have answers maybe a bit later.
Thank you.
Thank you.
Okay, next speaker is Jean-Baptiste Joly, who is going to tell us about rotation curves and dark matter fraction.
All right, thanks a lot. So hello everyone, my name is Jean-Baptiste Joly. I'm a postdoc at MPE in Munich. First, I'd like to thank everyone for the nice invitation to get to talk about my work. Before I start, a very brief disclaimer that everything that you'll see now is very much ongoing work, so please keep that in mind. And the talk is going to be mostly about methods. So yeah, I will talk a lot about rotation curves. So first, a little bit of context. So why do I actually care about rotation curves? So rotation curves, as you all know, were the first direct evidence of the presence of dark matter, and that's what you can see here on this plot. As you all know, if we have only normal matter in galaxies, then the rotation curve should behave something like this. So as we go to further and further radii, the curve will tend to go down, but what we observe is actually something that flattens out at large radius, and this is due to the presence of dark matter. So that's why it's very important to study the rotation curves themselves, and more specifically the shape, in order to probe the presence of dark matter and its fraction within galaxies. So now that's for local galaxies, but what's the story at high redshift so far? So here I show a plot from Nestor Chachard 2023, where they studied 100 galaxies at redshift between 0.5 to 2. And the important thing to note is that on this curve, you can see things that are kind of flat, and also some other which seem to be maybe dropping. And so one wants to study these shapes in order to know what is the corresponding dark matter fractions. And one issue with this type of work, which of course is state-of-the-art, but still it only extends to about 2 RE, where RE is the galaxy effective radius, so it's basically how big the galaxy is. And if you remember from the previous slide, the effect of dark matter is going to be most prevalent at large distances from the center. So that's why it's actually very important to probe these curves at large radii. The problem is that at high redshift, or higher redshift than local galaxies, it's very hard to do because you need to detect the line far away from the center, and that takes a lot of integration time. So you can, target a few objects for a very long time and try to get these curves, or you can use techniques like stacking. And that's what I'm going to describe now. So spectral stacking, just as a reminder, is a technique which basically allows you to boost the signal-to-noise ratio of your observation. So if you have a lot of spectra from, let's say, a lot of different galaxies, and the spectra look like this, so basically mostly noise, but you know that there should be lines, emission lines within the spectra. So let's say H alpha line from all of these galaxies. If you know where this line should be located, what you can do is basically align all these lines together on the expected position. And then what happens is, because the noise is random, and so one times up, one times down, on average it's going to go to 0, while the spot where you actually have the line you'll see the line appear. So this allows you to get a much better signal-to-noise ratio of the line and get you the average emission line from your object. The problem is that, as I mentioned, this requires to have the line center in order to actually align the line together. And in this specific case of rotational curve studies, the center of the line is actually what we're looking for. So one might wonder, is spectral stacking actually suited to study rotation curves? And okay, so at first you might think it's not, but then I took the problem the other way around. If you know where the lines are located, then you manage to get the perfect stack. So then if you actually manage to get the perfect stack somehow, then does it mean that you actually get where the line are located? So that's the whole idea behind this project, where basically what we try to do is we get random position of the line, as you can see here, and as the line gets more and more together, you can see that the stack is maximized. So that's basically the idea behind the algorithm. We take some random tone spectra with noise, we shift them around, and we try to have them maximize the stack. So now to apply this algorithm, we applied it to some data, of course, and this is a sample of 218 galaxies from the CHEMOS 3D survey, which is roughly 700 galaxies. And we selected these galaxies such that they have roughly regular rotation from the existing rotation curve that, again, don't extend very far. And also they have JWC images where they look like, normal rotating disks. So basically not including everything that would be mergers and whatnot. So that's the sample, which is observed in the H alpha and N2, by the way. And then on top of this, in order to test the algorithm, we produced some mock data. So this was made with Dismal Pi. And so I generated some mock cubes, which basically have the same, of galaxies that have the same properties, so star formation rate, stellar mass, RE, etc., as the galaxy in my sample. The same also observational properties, so that means field of view, spectral resolution, and whatnot. Also H alpha and N2, and most crucially have the similar signal-to-noise ratio as the data. So now that I'm armed with the data and the mock data, I'm going to explain briefly how we proceed with the data extraction. So you can see here the galaxy, so H alpha flux. What we do is we put a slit, which is aligned with the main axis of rotation of the galaxy, and we split it in a certain number of bins. The bins are split basically as a function of RE, and you can see that we go basically from 0 to 5 RE and minus 5 RE. From each of these bins, we extract some spectra, and as you can see in the center, we have a pretty booming line, and as we go further and further away, the line starts to disappear because, of course, signal-to-noise ratio of light. So now that we have these, basically for each of our galaxies, we have 11 spectra, and then what we do is for each galaxy, we stack all of the spectra from 0 RE together, then add 1 RE, all the galaxies together, etc., etc. And so that's basically what we do. So now about the algorithm itself. So the idea is quite simple. Basically, the first step and the building block is that for each of the galaxies in the sample, again, at a given RE, we'll generate a random set of velocities, one for each object, and this is the position that we'll use to center the line and to then produce the stack. So once we've done that, we can produce a stack, and then the issue is that we need to be able to tell the computer that this is good and that this is bad. So how do we do that? How do we explain that this is a nice resulting stack and that this is not? So for this, we need to apply some grading function. And the grading function is a bit complicated, but basically it consists of a few main things. The first thing is the amplitude of the line, of course. So we fit it with the Gaussian. We check how bright the thing is, and that's going to be a first ingredient to our grading. The other thing is the line width. And you can realize how important it is because if we just use the amplitude, for example, then what the computer is going to do is that it's just going to look for the brightest noise peaks in your data and then align them all together. But if we put a certain limit on the width, then it's going to already force it not to just take the brightest peak and put them together. Now there are a few other subtleties. One of the main one, which again goes into the idea of not wanting to create just some bright booming line by aligning random noise realization, is that on top of using this main slit that I described earlier, we use two additional slits. that are offset by +10 and -10 degrees. And this allows us to probe different noise realizations. And so basically we perform the exact same analysis on the 3 different slits. We stack them not together, but independently. And then we compute the grade independently in these all 3 different slits. And now if you had a specific noise realization that would allow you to get a booming line in the central slit, for example, it's going to be hard that this specific configuration will also make a line in the other things. While where the line is, it's going to be, you'll have the line at the same spot in the 3 different slits. So that was one of the first things. Now something else is that instead of stacking the H-alpha line, forgot to mention that we're stacking the H-alpha line, so instead of stacking just the H-alpha line, we also stack the 2 N2 doublets. So we stack the doublets together, we don't stack it with the H-alpha, but we stack them together, and we produce the same type of analysis, and now this is yet another noise realization because we are probing another part of the spectra, basically. So we do the same business of grading the stack, etc., but now on the N2 doublet, and the final grade is going to be a combination of the H-alpha and of the N2. Yeah, something very briefly, in order to actually make the algorithm go to be maximum, we use the genetic algorithm. Sadly, I don't have time to go through the details now, but if you want to discuss, I'm happy to talk about that. Now, just about the results themselves. So the first thing that we did is, because we have the mock object, we know exactly where the line should lie. So what we can do is try to see how the grade function evolves as we stack more and more line well in phase together. And that's what you can see here. Okay, you cannot see the thing here, but basically it says percentage of the sources properly stacked. So here is 100% of the sources that are stacked where they should be. And as you can see, aside from a few hiccups, which, okay, again, work in progress. But as you can see, as more and more sources are stacked well in phase, we can see that the grading function evolves. So that was very good. And now, of course, we can try the real thing, which is to get, with the mock data, get the average rotation curve, because again, we know where it is, and try to compare this to what we get from running the algorithm. And that's what you can see here. So you can see behind the real and median values, and on top the measured one, so you can see that they agree very well. At the bottom, you can see the difference, the channel difference between the two. And you can see that these always lie between the 5-channel regime. And these channels have actually been oversampled 5 times. That means that in the end, the final product that we get is always roughly 1 channel within the 1-channel limit between the measured and the real thing. So that's basically as good as it gets. So now it is very much ongoing. I just did this very briefly before coming to the conference, but I just want to show a bit of an idea of what we would get when we apply it to real data. So that's a very preliminary result, but just to show very briefly, for the sample that I mentioned earlier, so you can see that we go from -5 to 5 RE, and it seems like we see some slightly declining rotation curve, but again, very much in progress, so stay tuned for further results. So, okay, briefly with the conclusion. So what did we do? We extracted data from the COSMOS 3D survey up to 5 RE. We produced mock cubes to mimic this data. Then we produced the algorithm, which is nearly completed. Still a few tests that need to be done, but it's basically there. And now we are applying the algorithm to the real data. Just a very few things about the next steps. The first thing is about spatial normalization. There is a whole debate, let's say, about how you should normalize, whether you should use self-scale or stellar scale, so basically whether you should use RE or the turnover radius for the rotation curves. Now I'm using the stellar scale thing, but I definitely want to test both methods to see which one is more suited for this type of studies. Given that the sample is pretty big, one thing that we can also do is to try to see if we can see some type of redshift evolution of the shape. And then again, with the mock data, we could try different input shapes, so whether we have a dropping rotation curve or flat rotation curve, and see how the algorithm reacts to these. And probably more things that I haven't thought about yet. So yeah, that's it. Thank you.
Thank you very much. We have time for one quick question.
a question about all the, you have to do a lot of normalization on the scale, validate template, and you also apply some cuts. And could it generate some biases? Because every time you apply a cut, you kind of cut the distribution. If the noise go one way, it enters and it go out, so it can create extremely nasty features. Is it something you can test ultimately with your end-to-end simulation? And in the end, you show big error bars on your preliminary results. Is it the 1 sigma? In this case, you cannot say anything, or is it more?
So the error bars now, again, very preliminary, but the error bar is basically the distribution between all of the different rotation curves, because this is an average from 218 rotation curves, right? So what I show is basically a standard deviation from all the curves that are included to get the average result. And to answer the first part of your question, yes, there are lots of biases involved in this work, and that's why we are really putting an effort on testing with mock data, because now we can really, have a good handle on what we input and try to see what we recover as an output and try to modify a bit just to make sure that everything works. Yeah.
Yuki, you had a question?
I think if we are tight on time, I'll just ask her.
It's a short one. Okay. Okay, so let's go ahead. Thank you again.
Thank you.
Should be like a hide floating controls, but it's not there. Just push it in the corner. Yes.
Okay, our next speaker is Juan Manuel Pacheco Arias, and he's going to tell us about specific angular momentum maps from nearby galaxies.
Thank you. Good afternoon, everybody. My name is Juan Manuel. I'm a PhD student at LAM under the supervision of the Professor Philippe Ram, and today I'm going to present to you the preliminary results of my PhD thesis in the computation of the specific angular momentum maps for nearby galaxies. So let's start by defining the main quantity of this stuff, that is the angular momentum. So the general description for the angular momentum of a stellar component in a galaxy is this one over here. As you can see, we will need to have a 6-dimensional space information to compute it properly, because we need the 3 positions, the 3 velocities, and also the 3D mass density distribution of the galaxy. Of course, this is not possible in observations, it's just possible for simulations. So what people have been done since the 80s is to take a set of assumptions in order to compute it for images. So the first thing is that we usually compute the specific angular momentum, that is the angular momentum normalized by the mass of the stellar component of the galaxy. At the beginning, they assume that there are not radial motion and not vertical motion in the galaxy. All the motion is just tangential and is just depending on the galactic plane coordinates. And we also assume that the 3D distribution of density, of mass, is the surface mass density multiplied by the vertical component. But if we assume that the vertical component is symmetric along the galactic plane, we will end up with an equation like this, where we just have one vectorial component of the angular momentum that is along the perpendicular direction to the galactic plane of the galaxy. And we can see here, recognize the usual terms that we use to compute the normal angular momentum, that are the mass, the position, that in this case is the radius, and the velocity, that is the initial velocity. When they start doing this in the 80s, this formula was still complex, so they wanted to have like a approximation derivation of the total specific angular momentum, and they did that using this formula. So they say, okay, we will say that the specific angular momentum is just a coefficient that will depend on the morphological type of the galaxy times a velocity, that is a representative velocity of the rotation curve, and a representative radius. So using that definition for the total specific angular momentum, Fold in 1983 derived the Fold relation, where he compared the total specific angular momentum against the stellar mass, the total stellar mass, and he obtained this relation over here. It follows a power law that it was also predicted by the lambda CDM cosmological model, and the slope of that power law is predicted to be 2/3 based on the standard cosmological model. And for spiral galaxies that are here located, the non-field points, he arrived to a slope that was close enough to what is predicted. As you can see here, if you compute the total specific angular momentum for the elliptical galaxies is a little bit lower, so he was also able to distinguish in this plane the two morphological types. But nowadays, we know that we can go even further. So the first thing that we can do to compute the angular momentum is to get rid of the assumption about the velocities and to say that we will have the three components, the radial, the tangential, and the vertical, still along the galactic plane. And if you still use the assumptions for the density, you will derive a formula that we are proposing here, an extended formalism, where you just recover the vertical component as always, but now you include the x and y components that will be the angular momentum that is stored in the galactic plane. Usually, it was assumed to be negligible and zero, so we wanted to test if that's true in our case. So to do so, we use a sample of 31 galaxies presented in the Corsaga paper that I will explain in the next slide. In those samples, we obtained the mass distribution using the WISE-W1 band photometry, and we have also the surface brightness model split into the disk component and the bulge component. The mass to light ratio was derived using color subtraction. So after that multiplication, you will have the surface mass distribution, and the velocity components, we have two things to extract from it. We have also the velocity map for each of the galaxies in the H alpha, and we have the rotation curve using H alpha, that is until this point, and then extended using H1 kinematics too. So in this case, we will use the rotation curve as the tangential velocity component, and we will subtract this rotation curve from the velocity map to get an estimate of the vertical component of the velocity. So these are like the main three samples that also compute the angular momentum for nearby spiral galaxies. We have Fall, Romanowski, and Posty. In the case of Fall, you can see that the slope is very similar to what is expected, that is 2/3. And in the case of Romanowski and Posty, they are very similar between each other. And then when we plot on top of this the total angular momentum of the vertical component for our sample, we can see that it's matching the slope more or less of the previous two studies that are more recent. So the very important thing about this new extended formalism, apart from the angular momentum along the galactic plane, is that now, apart from computing the total angular momentum, we can see its spatial distribution because we can compute it pixel by pixel. So in this case, I show you like the three predominant structures that we found in our sample. We have these three galaxies, and what you can notice here is that most of the specific angular momentum, the vertical one, is located in high density regions. So we can here see clearly that most of it is located in the bar, here in these green spiral arms, and also most of the galaxies, most of the angular momentum is stored in the clumsy regions that are very far away from the center when you have high rotation curve. So this is something very interesting we just realized, and we want to quantify how much of the angular momentum is stored in each of the morphological structures of the galaxy. Now we can move to the second part, that is to determine if the angular momentum on the disk plane is relevant or is not relevant. So we know that the velocity along the line of sight, the velocity map that I showed you before, is the combination of all the components plus the systemic velocity. So we have this map, and we can create the velocity model knowing the rotation curve and the systemic velocity. If you subtract that, you will end up with something like this, that is the residual velocity map, where you have combined the radial velocity, the vertical velocity, noise, instrumental effects, etc. In this case, we wanted to do an approach to compute how much of the angular momentum will be on the disk plane as an upper limit if we use the whole residual velocity map as being produced just by the vertical component to see more or less what we can get. And when you do that and you integrate to obtain the total angular momentum along the x component and y component for the Corsaga sample, we found that first the limits, the maximum values that we can obtain, are very low compared to the ones that you saw in the previous plot about the vertical JZ component of the specific angular momentum, and also the mean value is more or less around 0. So this is still a small sample, it's just 31 galaxies, but we show that here the specific angular momentum is in the display is negligible as expected. And also we didn't see any trend in their maps or any trends. For example, if we compare this quantity with the mass, with the radius, there is not a clear relation like in the other case. So to conclude here, the main things is we were able to recover the slope of the fault relation for the Gonzaga sample in this case. The most important part of this is that using the angular momentum maps, we were able to identify that the angular momentum is located in the high density regions of spiral galaxies. And finally, we propose the extended formalism to show that the angular momentum map on the disk is negligible and there is no clear trend on this sample. So the perspectives for this work are to, as I told you before, first to quantify and characterize how much of the angular momentum is stored in each of the spatial features and how it's distributed, apply it to a larger sample, and also to validate this formalism using mock observations, because in mock observations of simulations you can disentangle clearly the radial component for the vertical component, and you can do it like knowing which are the results previously. So thank you.
Thank you for this nice talk. My question was, you showed that you analyzed a sample of galaxy that had a bar, right?
Some of them.
Some of them,
yes.
Right? Does your sample of galaxies contain warps of the disk? Because if they do, then that could also, does it affect your analysis?
So far, to see the warp, we will need to do like the other map, the X and Z map, but I didn't check yet how much of the galaxies have a warp in the sample we are.
But does that affect your, so when you look at the motions in the Z plane, do you
if they have a warp, that will be an indication that the vertical motions are very important for the galaxy. So that will be an indication that this component of the angular momentum can be enhanced. Yes.
But do you see that? That's my question.
No.
Okay.
We have a question in the back.
Yeah, thank you for your interesting talk. Have you considered the possibility of testing your methodology on the Milky Way? Because we have 6D, so 3D positions and velocities for about 30 million stars in the disk, and you could test if your second conclusion there is true also for the Milky Way, I think quite easily, and you can disentangle the vertical and the radial components of the velocity.
Okay, I didn't check yet.
It
I'm
would be-
thinking about it. Thank
Just
you.
a suggestion.
Perfect, thank you.
Any other question? If not, let's thank the speaker again.
You need 20 minutes on the Zoom. Take this one. Like this stuff. Okay.
So the last speaker of today is Johan Dubois, who is going to tell us about galaxies with brains.
Your favorite topic, dust. So I'm going to talk about a new implementation of dust physics for galaxy formation in the Ramsey code that we've been doing over the last couple of years with colleagues that are listed here. So why care about dust? Because it's fun, first of all. Second of all, for a few other reasons, the self-fitting, the dust in self-fitting is very important when you want to reconstruct galaxies. You have to know about the attenuation law in general. You have to come up with a given attenuation law. Dust intervenes also in feedback processes with the coupling of radiation, for instance. This modifies also the cooling in the ISM, because if you lock some of the metal elements into dust grains, that some metal in the gas phase are not available anymore. Okay, so they change the cooling rates, for instance, and other processes like H2 formation on those grains. And so we can, from observation, reconstruct several properties of grains, including dust to metal ratio in the ISM, the fraction small grains, what is the chemical composition, this kind of stuff. And my main focus for this talk will be about exactly this thing, extinction curves in the local universe, so the extinction curve of the Milky Way and of the imaginary clouds. Okay, try to explain why they are as we see them. Okay, and there has been a regained theoretical interest with hydrodynamical simulation in the recent years, with a few of those groups that have investigated how dust grow in galaxies in general. Okay, so that's typical extinction curves that you can see. I think it's a laser pointer. Yes. Okay, and you have the typical Milky Way curve that you see there, the LMC, Large Magellanic Cloud, and the SMC there. Okay, and you see the steepness of the curve. Everything is always normalized to the V magnitude, which is around here. Okay, and you see that the SMC, LMC are steeper than the Milky Way. Okay, and this is known for a while by the work of Matisse et al. And from Drain, that those extinction curves, their shape stem into the grain size composition and into the chemical composition of the grains. Okay, and I will try to explain why they are like this in galaxies, in the different galaxies. So we have been modeling these different things in the Ramses code. So this is a typical galaxy we simulate. So we model the accretion of grains into the dense phase. So I try to color code which process happens in which phase of the ISM. Okay, so accretion proceeds into the dense star-forming gas, typically above 10 particles per cc, together with coagulation of grains. So coagulation is just two small grains, typically a few nanometer size, that collide and form bigger grains and so forth, and grow to larger sizes. There is the process of releasing the small, the grains into the ISM, the seeds of grains in the ISM by stellar ejecta. This includes supernovae, but also AGB stars. Okay, and this is released a bit everywhere. You have star formation, but then it takes some time for the low mass star, AGB stars, to migrate away from the dense star forming clouds so they can release their ejecta completely elsewhere. And then we have shattering in the diffuse medium, which is typically around 1 H per cc, roughly, which is two big grains, microns, fraction of microns. They collide at high velocity, 10 kilometers per second or more, and they shatter into smaller fragments, into small pieces of nanometer grains. Okay, and then we have finally the thermal sputtering and the inertial sputtering, which is just destruction of grains by supernova explosions, okay, by the ramp pressure of supernovae, by the shock, which happen mostly into the very diffuse, hot, extra bright gas, like in these hot pockets that you can see there. And we have all these cycles, and we separate between different composition, different sizes of grains, and different composition of grains into silicate grains and into carbonaceous grains. So the numerical setup is the following. It's not a cosmological simulation at all. We start with a thin disk initially, surrounded by a huge halo that doesn't enter even in this hole. So you have a very large halo that hosts the disk. We varied the mass of the halo and of the disk. We varied the gas fraction. We varied the initial gas metallicity. And a typical resolution of decimation is 20 parsec, but we varied from 10 to 100 parsec to see the effect of resolution. Okay, and the typical physics there is that we have gas cooling, star formation with a Schmidt law, and the feedback from stars, including type 2 supernovae, type 1a, and so on. So these are maps of the gas density, temperature. So remember, this hot diffuse pocket is very hot. It's extra bright at 10 to the 6 K or so. This is the dust to metal ratio in a Milky Way-like galaxy. This is dust to gas ratio. This is the fraction of small grains. Red is a lot of small nanometer grains. And in here, it's the fraction of carbon grains over total, right, versus silicate. Okay, and what you see, which is interesting, is that in the dense gas, the fraction of small grains is pretty low. Okay, it's bluish, intermediate, depending on exactly where you are. In this intermediate diffuse gas at 1 H per cc, you have a lot of small grains. It's getting higher, okay, because of shattering in that region. And in this region where you had recently supernova explosions, the fraction of small grains is dropping because thermal sputtering is much more efficient at destroying the small grains than the large grains, okay? So only remains the large population of grains sizes. So this is dust to metal ratio of this Milky Way-like galaxy. Very quickly, it increases its dust to metal ratio at around the canonical value for the Milky Way, around 0.4. Okay, and you see distribution between carbon grains in blue, silicate grains in red, and decompose into small and large population of grains. So small is 5 nanometer, large is 0.1 micron. Okay, and thanks to that, we'll see after, we reproduce the extinction curves, but here you can wonder which is the dominating process that regulates the mass of grains into the ASM. And here we just measured from the simulation the growth rate of or destruction rate, depending on the process, of the different components. And what you see up there in black is the accretion rate, in solid black, that's the accretion process. In dark blue, it's the coagulation rate, and in light blue, in cyan, it's the shattering rate. And all other components are below, typically. So the dominant channel for growing dust into the typical Milky Way environment is not released by stellar ejecta, it is the growth through the ISM. Okay? Just atoms in the gas that collide with grains and puff up the grains and make them grow faster. And then there is this regulation, this kind of equilibrium between coagulation and shattering that will set up the structure of the sizes of grains into the ISM, the famous MRN distribution. Okay, so now let's try to measure extinction curves. So just be a bit careful. Extinction is not attenuation. I repeat, extinction is not attenuation. We always do the confusion. Okay, it's completely different things. Extinction is you take one single star, it goes through a slab of gas, and you measure the extinction. Attenuation is you take a big collection of stars that you don't resolve, like in distant galaxies, and you build up through radiative transfer effect the final attenuation, and it can be completely different from the true underlying extinction properties of the ASM. Okay, and so basically to get the extinction curve, you convolve the size of the surface of grains, their number density, with the optical properties of grains. This is for large grains, this is for small grains, this is just data taken from the database by Bruce Drain and Weingartner. And when you do this little exercise, you can produce extinction curves, okay? And the solid black line that you see in thick here is the result from this Milky Way-like simulation. We reproduce the Milky Way extinction curve. We reproduce this famous bump at 2000 angstrom, which is basically just this little thing, this little property you see in small carbon grains in the optical property of the grain. It's just this thing that you see there, okay? And you see the decomposition in terms of different contributions from different grain population. Indeed, the blue dotted line is the small carbon grains that produce that bump here, and the silicate are responsible for the slope. They are the small silicate grain, which is the dotted line that is here. Okay, and that's the size distribution, which is close to MRN. There's nothing new here. We knew that we need MRN to get the Milky Way extinction curve, okay? And that's nice that we reproduce it in the simulation. That's consistent with previous findings. Okay, so now we look at a different galaxy simulation. We reduce the mass of the halo and galaxy by a factor of 10. That's the meaning of G8 here. That's the galaxy mass. We change the galaxy gas fraction, like Hg is for high gas fraction, Lg for low gas fraction. We vary the metallicity in solar units there. And you see you have different structure of the ASM, that's the gas density and the dust to metal ratio. And so we played with many of those kind of galaxies, and basically we try to see if we are completely, if we are within the bounds of the dust to gas ratio observed value, dust to gas ratio, dust to metal ratio as a function of metallicity, and we'll see we're doing quite okay. And here you can see the depletion, in particular of iron, and the depletion of carbon in the ASM phase. So the larger the value, the more carbon in that case are within those grains. Okay, and you see that there's a nice transition at different metallicities for silicate and carbon, and that will be important for explaining the extinction curves in particular. So we looked at different extinction curves. So I won't show you each one by one, but there's a nice way to get a summary of those curves. Is you try to compute the slope. So in general, you take it around here, but you can take a different value if you want to play this little game. But typically, that's the value when it's renormalized to AV. It's the value that you spot here. Okay, and then you can measure the bump with this little thing. Okay, but basically that's the bump strength is this thing, and we measure it for all our curves. We summarize it here. That's the bump strength versus UV slope. Milky Way, the observed value of the Milky Way, its average value is there. All the dots, it's individual sight lines in the ISM. Okay, so the average is here. LMC, individual sight lines, the average value. SMC, individual sight lines, its average value. And that's all our different simulations that you see are scattered in that plot. So let's try to make sense of this thing. And here it's color-coded by metallicity. Okay, and you see the metallicity, it's low metallicity, percent of solar there, and it's increasing. So the lines are connected because it's just the time that is increasing in the simulation. It's getting enriched by supernovae typically, and so the metallicity changes, and you see that there's a kind of pattern. When you increase the metallicity, it does that, right? It increases the UV slope, and then it increases the bump strength and decrease the UV slope when you go to higher and higher metallicities. Okay, so again, it goes that way. So here just the previous plot that you see, but decomposed into different contribution to the growth of carbon grains by accretion in color, by ejecta with the size of the symbol. So it's a bit complicated plot. So we'll try to summarize quickly, but if you're more interested, look into the paper. And here the same kind of quantities, but for silicate grains. Okay, and if you focus now onto the carbon grains, all those simulations that are here at the bottom, the amount of carbon grains are dominated by the ejecta of supernovae and of stars. Okay, so you have a low bump strength because ejecta preferentially release large grains, 0.1 micron grains. Okay, and then at some point there's a turnover, the accretion kicks in. You produce more carbon grains by accretion than by ejecta, and then you produce small nanometer grains, and the bump strength is reinforced. So it's going up. Okay, that's the important thing here for that component. And then you do the same thing for silicate. You remember silicate, the depletion of iron, which is a tracer of silicate grains, kicks in earlier as a function of metallicity than for carbon. So very quickly, you increase the silicate accretion with the metallicity, and you go to the right because the small silicate grains produce a steeper slope. Okay, so you go to the right, and then you increase again the metallicity, and you're completely saturated into silicate grains. And the only thing you can do is coagulate those grains. And by coagulating, you produce bigger grains, 0.1 micron, and you reduce the slope because you remove the small silicate grains that are responsible for the steepness of the UV slope in the extinction curve. Okay, so that's the summary. I won't comment there. If you're interested, you can flash code this thing, and you will access the paper. I will stop here. Thank you.
Questions?
I can hear you.
I have a question about so you tell that the AGB stars are not so important, and for very icy dusty galaxies there was a lot of debate about the need or not to have AGB to get very dusty systems. So if I correctly understand what you have shown, in 100 to 200 megayear you can get a dusty system if you form enough metal.
Let me go back to there. So basically what happens is that there's this kind of break in the relation. Be careful, because this break is largely artificial the way it's constructed from the data, first of all. But still you see that there's a change roughly in the distribution of points. And this happens because here above this metallicity of a few 10-20% solar, you're dominated by accretion. That's what we see from the simulation. Okay? And below this 10-20% value, you're dominated by ejecta from stars. So about high redshift, I don't want to be conclusive because it's very idealized setup we do here. Okay, we neglect there's no accretion onto disk, so I don't want to say that much about this, right?
Maybe a last question?
Yeah, so you studied the dust formation and trying to reproduce the acceleration. The flip point part of this problem is the amount of metals left or elements left in the gas. So in this slide you have the depletion of some elements, and there are lots of observations of depletion patterns in the ISM from stars.
So it's this plot. So we measured those depletion patterns. So for various elements, magnesium, iron, silicon, oxygen and carbon, and the default model, so one assumption of our model is that the chemical composition of silicates is frozen. We choose a composition and you cannot change it. It's like that. Okay, and we choose different composition. Our preferred one is this one, iron-rich olivine. Okay, and you see the depletion pattern. It's kind of okay-ish, except maybe for magnesium. Okay, it's a bit above, but for the others, the data is the data is very tricky because it's column density, and when you want to recast this stuff into volume density, you have to take into account that the gas is clustered in the line of sight, and so basically you need to compare to the solid lines that are there in black and red. Okay, and so we are above for magnesium, but the other element seems to be doing okay-ish, okay, in this different depletion pattern. If you change, what's nice here is that we showed that changing the composition has a strong impact on the depletion of the various elements. It tells you something about what should be the natural composition of silicates.
Okay, I think my question. What could be the origin for dust grays and elliptical galaxies?
It's a good question. Probably AGB ejecta, that's my 2 cents there. Because it's all population, it's not forming star anymore. There's not so much dense gas, so probably the AGB ejecta might be important, but this has to be looked at. There's not so much theoretical work actually in simulation looking at cluster of galaxies. I only know, I think, 3 of them. One is from Etienne Pointe-Coudreau from almost 20 years ago. And there's more recent work by Gergo and another one by Mark Folgersberger. And they looked a bit into that, into how much dust you end up with into the intracluster medium. I don't remember they looked into stellar ejecta versus accretion, but one important result from their investigation is that if you use standard thermal sputtering rates from the classic literature and apply them in your model, you completely fail at reproducing the diffuse infrared emission in those environments, and you need to reduce by 10 times the thermal sputtering rates, for instance.
Okay, so let's stop here. Let's thank Johan and all the speakers.